you actually want to learn the magic of predicting the product that may be formed in an organic reaction? Are you actually tired of always mugging up that this is the product that will be formed when so and so react with each other? No, because with general organic chemistry logic, you can very well predict that what is going to be formed, and also JEE asks so much of concepts involving and revolving around these GOC topics also, and this GOC will also be helping you to not mug up but understand all the later chapters of organic chemistry. But for this, you have to promise you will watch this video till the end, because our analytical guys have also told us that very few students completely watch the video till the end, and although we know only 1 to 2% of the JEE aspirants are going to actually get a respectable government seat in IITs and NITs, so if you are one of them, then go to the description section after finishing this video, comment that yes sir, I have completely watched the video. Do not worry about writing all these lecture notes, because these lecture notes and the hand-picked problems which we have specially picked up for you, you can always download all of them for free. From where? Just go to the description section. You will find a link to the amazing World of PW app, which is also helping millions of students every year like you to excel in their competitive journey. So let's dig into GOC. So the topics that we will be learning under GOC2 are: first, we will be introducing what a reaction mechanism actually is. Post that, we'll be discussing about the various electron displacement effect and their applications to decide the stability of reaction intermediates, the acidic and basic nature comparison of various compounds, and after that we'll be discussing about what actually are all aromatic compounds, because benzene is not only aromatic, there are various other aromatic compounds, because aromaticity is a basic definition. And after that, we will be using all those PYQs to which you must have felt, sir, why this came, why that came, all our logic. So we'll be applying all those GOC logic in your exact PYQs, which you will be directly getting in your JEE mains examination. Now, moving forward, and actually starting with what actually is a reaction mechanism. See, in organic chemistry, what we see, sir, you have a reactant, you mix two things. One reactant is called a substrate. Now, if you have two reactants, so which reactant will be termed as a substrate? That reactant is termed as a substrate on which the attack happens, attack of the attacking species. Now, who is an attacking species? A species which is deficient of electron, or it is having excess of electron. Because what is the beauty of reaction mechanism is, sir, it is nothing but attraction between plus and minus. What is plus? Nucleus never participate in a general organic reaction, because if nucleus would have been reacting, then it would be Hiroshima and Nagasaki. We will not be able to be present at that point of time to witness such a nuclear reaction, because nuclear reaction is of tremendous energy. So in organic chemistry, whenever we say plus, it means electron has left a specific orbital, and because of the deficiency of electron, there is a positivity that has been created because the inavailability of electron is there. So now in organic compounds, whenever you see a positive charge, that means electron has vacated that particular orbital. So what are attacking species? Attacking species are created by another reagent which gives rise to such a species which may be having excess of electron, or which is maybe deficient of electron. So that excess or deficient of electron species will attack the another reactant, and that another reactant to which the attack is taking place is called a substrate. For example, let's say I have an alkyl halide. Now, carbon is generally represented by R. This halogen, because of electronegativity difference, we know it withdraws electron from carbon chain and thereby creating a positivity in this particular carbon chain. Now let's say I have a reagent called NaOH. Now this NaOH can give rise to Na plus also and OH minus also. To which part I am referring as attacking species? Now we have to look into the reactant. Organic chemistry is all about carbon. So can you just check that in this carbon, what is there, sir? It is having a positive charge, as in it has a deficiency of electron. So if it has a deficiency of electron, which is represented by a positive charge, plus. So who attracts plus? Sir, minus attracts plus. So minus becomes our attacking species. And what moves? Electron moves from higher concentration towards lower concentration. So this minus will move from higher concentration, from the amount of NaOH that you have taken will produce OH minus. This OH minus ion will attack the carbon because it is having deficiency of electron, and this basic is known as reaction mechanism. Now let's say this chlorine is kicked by this attacking species. So this minus, when approaching this R, will kick out chlorine, which will be termed as a leaving group, and the product that you will be seeing is an alcohol in this particular case. But where our electron displacement effect come into picture is a reactant, I mean a set of reactants when undergo reaction and give rise to product, there is always a situation where transition of this reactant into product has taken place. Now that situation is termed as a transition state where a reactant has been converting into a product. In that transition state, intermediates are produced. Now, in order to have a clear picture of those intermediates, you must have seen a Salman Khan film. Salman Khan giving a punch to his villain. The villain ultimately, after receiving that punch, is gone. But in the very slow motion side of cinematography, when the photographer or the camera person is trying to show you that the impact of the punch is this much of amplitude, that if it is hitting to the villains at this rib area, the whole of the bones cage has been ruptured, which is shown by the zoom in and slow motion of the camera. So that zoom in and slow motion of the camera is happening in fraction of seconds. But in order to actually understand that why the villain has passed by just a punch, they show the impact using the slow motion, which is happening in a very fraction of seconds. Similarly, reactant is converting into a product in fraction of seconds. But in that fraction of second, a transition state is always come into picture where intermediates are formed. Now, this intermediate formation can be a one-step process, can be a two-step process, can be a three-step process. I mean, various intermediates can be produced. Sir, what all are the number of intermediates produced? That is specific for specific type of reactions, which you will be doing. But what I'm trying to tell you is these intermediates can be isolated, that how many of them are formed, and through the beauty of reaction experiments, this chemical kinetics graph will also help you to understand the very basic common sense. What is it? Whenever a reactant is converted into a product, now we have already seen thermodynamics, this is energy. Those who have not seen it, I'm taking a basic. Enthalpy is nothing but energy. Let's say reactants has some energy, so this represents summation of an energy of reactant, and this represents summation of energy of product. Whenever a reactant is converted to product, the reaction may be endothermic, as in products is having more energy, or it may be exothermic, as in products is having less energy. Whatever may be the case, a reaction always proceeds like this. If it is an endothermic action, then also, and if at all it's an exothermic reaction, then also. Any reactant gets converted to product, any type of product, endothermic product or exothermic product. Product is always formed when these reactant species attained a maximum energy state. This energy is known as activation energy, and once activation energy, all the reactants cannot form products. Only those reactants can form products whose intermediate has the capability of riding onto the top of this mountain, this energy mountain, all the reactant molecules cannot climb this mountain. But all those intermediates, reactant will form an intermediate in the transition state. So who all intermediates that are capable of climbing this mountain, only those intermediates can form product. And obviously you must have gone to a water park. If you are climbing into a very dramatic and enjoyable slide, the time you take to climb up to that particular area is much higher. And while riding the slide, the time duration is very less. Similarly, when a reactant forms the most appropriate intermediate who has the capability to climb this activation energy barrier, this time is the maximum time for the progress of a reaction. Let's say a reactant is converted into a product, let's say in 10 seconds. So approximately maybe 8 to 9 seconds the reactant must be taking to reach this activation energy barrier, to cross this activation energy barrier. And in just a matter of 1 second, the product will be formed. So maximum time is decided by this intermediate. Sir, so that means intermediate, you are saying so many times. What all concepts decide that whether an intermediate is stable or not? Your electron displacement effects. So therefore, if you understand these electron displacement effect, you understand that how that Salman Khan punch to a villain is happening. So that zoom in analogy, that zoom in analytics, you can only do in organic chemistry once you know everything about who all are attacking to reactant on what side and why. And once that attack is catered, what is the product formed will be decided by the quality of reaction intermediates. Now, what is a chemical reaction at first place? So old bonds will be broken and new bonds will be formed. Now, ultimately, bond will be broken at first place. So our next topic becomes what are the types by which a bond can be broken. So a covalent bond can be broken by two types. It can be either broken homolytically, it can be either broken heterolytically. So a homolytic fission is that when you have constituent atoms like you have A and B, both of these atoms must have formed a covalent bond by sharing of electron. If they have equal distribution of electron among them, A has taken its electron and B has taken its electron, it is shown by a half-headed arrow. And the intermediates they form, the reaction intermediates are, once the bond is broken, then the other bond will be formed. But once the bond is broken, intermediates are formed. And these intermediates are called free radicals. And remember, the electronegativity difference between AB may be high or may be zero. So homolytic fission can take place with any. Generally, some people think that only those species can form intermediate who are all of equal electronegativity. No. Electronegativity difference has got nothing to do with whether a fission is homolytic or not. Actually, homolytic fission is favored by, first, whenever sunlight, remember from atomic structure, the amount of energy sunlight bears is represented by the frequency of electromagnetic radiation. So sometimes the question also writes h nu, which represents the packet of energy that is received by the incoming sunlight. So presence of sunlight always favors that bonds are broken homolytically. High temperature always favors homolytic fission. Electrolysis, whenever you pass current, homolysis take place. Whenever there is a presence of metal, homolysis take place. If another free radical is present, then also it will break a bond, it will try to create a bond fission as it is. If attacking species free radical, it will also create free radicals. So homolysis will be definitely taking place. And last but not the least, in generally all reaction takes place in universal solvent water. But if at all a reaction is taking place at gaseous state, then that gaseous state fission will always be homolytic. But thanks to the mother nature and thanks to your NCRT and thanks to your JEE community, the question which JEE boards, mains, advanced ask is, In nature also, you get homolytic fission. Let's say you analyze 100 reactions, so out of them maybe 5 to 6% of the reactions may be involving homolytic fission. Maximum fission what takes place in our chemical reactions also, in our types of question also, is a heterolytic fission, which is basically when two atoms are there and covalent bond is broken between them, then an unequal bond electron cleavage take place. As in, let's say A and B are undergoing heterolysis. So A, let's say, has lost the battle. So these both the two bonded electron are carried by the another species, that is B in this case. So A becomes a cation. So whenever heterolysis take place, you get a cation and you get a anion. So obviously here the favorable condition will be, obviously, if at all heterolytic fission is taking place, the atom who is more electronegative will take away the bonded electrons and will form the anion, while the other one will form the cation. Now, actually, heterolysis takes place, you have to form plus minus. So plus minus are ions. Ions are formed in which solvents? Are like dissolves like. So polar solvent favors the fission by which cations and anions are produced. So heterolytic fission is favored in the presence of polar solvent. What is the universal solvent? We have water, but because we know organic compounds are carbon containing compounds, so they are covalent compounds, and water is a polar solvent, and covalent compounds are supposed to be a basic non-polar compound. So organic compounds are also soluble in organic solvents, and famous example of organic solvents are alcohol and acid, ethers, acetone. There are some other solvents also, but all those solvents that are polar, because although alcohol and acid is an organic solvent, but because they also have got the ability to form hydrogen bonding, so they are also organic solvent, but of decent polarity, not that much polar as water, but still because they are polar. So in polar solvent, heterolysis or heterolytic fission is predominant. Moving ahead. Now, sir, once the bond will break, intermediates will be formed. Yes. What are these intermediates? The three intermediates to which I have marked as green are the intermediates which you have to remember, and you have to know everything about them because loved by JEE mains. Yes, there are other intermediates also like carbene, nitrene, benzene, but we will be discussing them in the later chapters because they are basically an advanced topic. Not very difficult, but because we are falling short of time, so why invest time in those topics which have low possibility or low probability of coming, and more or less advanced, they are loved by good topics. So what intermediates you have to know? Carbocation, carbanion, and carbon free radical. So discussing everything about them. Now first, talking about the carbocation and electronic configuration. Sir, we already know carbon has what electrons participate in bonding? Valence shell. So what is valence electronic configuration of carbon? 2s2, 2p2. But in order to form bond, 2s electron gets excited and you get 4 unpaired electrons. So this is 1, this is 2, this is 3, and this is the 4th electron of carbon. But this carbon has formed how many bonds, sir? It has formed 3 bonds with hydrogen. So let's say I mark this hydrogen with this different color. So there are 3 hydrogens, and this is pairing by 1 hydrogen, by another hydrogen, and the 3rd hydrogen. Sir, but this carbon has lost 1 electron. So this electron has been given by the carbon to somebody else, and thereby it has formed CH3+. So this will be the electronic configuration of this carbocation. It may be H, it may be some other combining atoms. I have taken the simplest possible case in order to let you know what a carbocation electronic configuration is. So carbocation has 1 empty 2p orbital. So how many sigma bonds it is making? 3. So 3 sigma bonds. How many lone pair it is having? 0. So its steric number will be 3. Hybridization will be sp2. Its geometry and shape both will be trigonal, planar, because it is a AB3 type of molecule with one vacant 2p orbital, and this vacant 2p orbital will have a tendency to accept electron, and a tendency of accepting electron is known as being a Lewis acid. So its nature will be it will be a Lewis acid, and it has obviously octet over here is incomplete, so it is reactive and it will react with another species to complete its octet. What about its magnetic nature? Sir, all electrons are paired. So if a species has all paired electrons, then it is termed as a diamagnetic species. What about the spin multiplicity? What is S? S is total spin. Sir, all spin are cancelled, so total spin is 0. So this mod of S is 0. So this is 1. So this is also termed as singlet. This is also termed as singlet. So carbocations are having what spin multiplicity? They are singlet species because it has a spin multiplicity of 1. Now, coming to carbon ions, sir, obviously we definitely know, you have given us that explanation that there are 1, 2, 3, 4 electrons of carbon. Okay, sir. How many bonds this carbon has formed? 3. 3 bonds formed with whom? 3 hydrogens. So 1 hydrogen, second hydrogen, third hydrogen. Fourth electron it must have got by reacting and mixing with other species. It must have got that extra electron. So this is 1 electron of carbon only, and it has received 1 electron from outside, the orange one. So this becomes the lone pair electron on carbon, because of which it is having an extra -1 charge, because this electron it has taken from another species. Some reaction would have taken place, and this carbon would have received that extra electron from the bonded atom and kicked out that atom as a cation. So this intermediate becomes a carbanion with how many sigma bonds? 3 sigma bonds and a lone pair. So steric number is bond pair plus lone pair, because there is presence of 1 lone pair, so steric number will be 4, and therefore hybridization will be sp3. So geometry will be tetrahedral, but shape we see with respect to nucleus. Geometry is tetrahedral, but shape is, there is a triangle in the base and a pyramid of carbon. So shape becomes trigonal pyramidal with a geometry of tetrahedral. Now, what about the octet, sir? Sir, its octet is also complete. All electrons are paired, so its octet is complete. Now, what about its, sir, but carbon is not an electronegative species. So if carbon is having an excess of electron, then it will definitely have a tendency to give these electrons. So its Lewis nature will be, it will be a Lewis base. So what will be its tendency to react? It will be reacting with another species who is having deficiency of electron, as in plus. So this minus will be getting attracted to a plus in that reaction mechanism logic of ours. Now, what about the magnetic nature? Because all electrons are paired, so it is also diamagnetic. What about its spell? Sir, all electrons are paired, so S is 0, so this is also singlet. Moving forward to the last one, which is carbon free radical. Now, sir, free radical, now this is very clear to us. Carbon was having 4 electrons. Now, this 4th electron I am already taking into the excited state, because it is an intermediate who has already formed a bond. So because someone said it is 2s2, but that S is, I am already considering the excited state, keeping in mind that you know chemical bonding, which we have already done in our previous one shots. If not, please go back and watch it. That's why in chemical bonding I said chemical bonding will help you, definitely help in inorganic chemistry, and it will also be helping you to learn organic chemistry. But over here I'm iterating that also, that carbon has electronic configuration 2s2 2p2, but it is, if it is forming a bond, then it will excite as 2s electron, so 2s electron is excited to 2p. Now, what are bonds? Carbon is forming 3 bonds with whom? 3 bonds with hydrogen, or with any other species it will form a single bond. So this electron will get paired, this electron get paired, this electron get paired. Now that electron, I'll just change its color. This red electron, it was of carbon only, but it is still unpaired, and because it is still unpaired, so carbon does not have stable and complete octet. So this intermediate will also be reactive and is termed as a free radical. So its electronic configuration is quite clear to you. It has 3 sigma bonds but there is no lone pair. There is an odd electron. Odd electron repulsion is not equal to that of a lone pair. Odd electron therefore is not considered by valence bond theory, and they say you do not consider it, so we didn't consider it. So number of sigma bond is 3, number of lone pair is 0, so steric number is 3, so hybridization will be sp2. Shape will again be trigonal planar, although there will be a repulsion of this odd electron, but this odd electron stays with unhybridized 2p orbital of carbon. It will not be getting the profit, the respect of acquiring a hybridized orbital. Now moving forward, what can you say about its octets? Now here octet is incomplete. Here octet is obviously incomplete. What about its magnetic nature? Sir, it is having one unpaired electron, so this will definitely be a paramagnetic species. And now many students confuse it all the time. Comment. You also comment in the description section what is its character, Lewis acid or Lewis base. Many students miss it and write something which you will be writing, but do have some common sense. Lewis said a base gives lone pair. An acid accept lone pair. It is having one electron. It cannot take two, neither it can give two. So it is neither Lewis acid nor Lewis base. A very common mistake will all students do. So if you also have done that mistake, do comment in the comment section, sir. We have also done it, but now we know that carbon free radical is neither a Lewis acid nor a Lewis base, because a Lewis acid accepts lone pair as in 2 electrons. A Lewis base donates lone pair as in 2 electrons. It is neither in those situations that where it can give or take 2 electrons. Now, about its multiplicity, yes, it is having one extra electron. It may be plus half, it may be minus half. In spin multiplicity, you anyway take mod of s, so mod of s will be, it can be plus half or minus half. Mod will be plus half only. So plus half, or I mean 1 by 2 by 2 is 1. 1 plus 1 becomes 2. So its spin multiplicity is 2. So it will be a doublet system. Moving ahead now. Sir, these intermediates are formed in the transition state, and when they are stabilized, they will decide what product will be formed. So sir, now this is a common sense. What is a common sense? That what can you comment about the stability of these intermediates? Let's say carbocation. Carbocation is electron deficient. So if you are electron deficient, if you have no food in your stomach, you want people to give you food. So you want people to be attached with electron donating group. Therefore, electron donating group will do what? Electron donating group will make carbocation happy. So carbocations will be stabilized by, if they are attached with electron donating group, then they are having deficiency of electron. They will like, you are giving me what I want. Similarly, carbon is already having an extra electron who's not electronegative. So carbon will try, you please take my extra electron and I'm carrying this burden, this luggage in the whole of the station. You please take my luggage and help me out to go to my car or maybe board the train. So carbon being not an electronegative atom would want someone to share those electrons. So who share my electrons? If I am attached with electron withdrawing group. So carbon ions are stabilized by electron withdrawing group. And what can you say about free radical? Again, people, generally a free radical can be thought of like a carbocation, but it is not always. Many students make this mistake, but you have to understand this, that free radical is a paramagnetic species. If it gains one electron, it becomes diamagnetic. Even if it loses electron, it becomes diamagnetic. So paramagnetic nature, that means you are getting attracted by magnetic field. Even if a free radical loses electron or gains electron, in both the ways it becomes diamagnetic. So because its situation is in between, therefore both the groups can stabilize a free radical. Yes, in your JEE mains question, most of the time you find such cases where a plus can be thought of a radical, but do not make this error in your judgment that they can only be stabilized by electron donating group. There are many examples, although of good questions, where electron withdrawing group also can stabilize a free radical. So how you can propose this thinking? Because free radical is a paramagnetic species. If you make a paramagnetic species diamagnetic, it always feels stable. So even if you take electron or give electron, paramagnetic species becomes diamagnetic, and therefore free radical is stabilized by both of them. Obviously, if I'm having plus and if you try to remove more electrons from me, I will not at all like it. I will be opposing it like anything. And similarly, if carbanion is already having excess of luggage and if you give me more luggage, I will not talk to you in my entire life. So I will not be liking that also. So these all are the cases of stabilizing and destabilizing the famous reaction intermediates. Now moving to, so now we know reaction intermediates also. Now the one more thing, because I have already discussed chemical bonding, two more terms, electrophile and nucleophile. What are electrophile? As the name suggests, electron loving species. Who all species are electron loving? Electron loving species are electron deficient. So normally we can think them of as plus. Now electrophiles are electron loving. Conversely, nucleophiles are nucleus loving. Now I will not go and react with a nucleus because organic reactions are not radioactive. But if we say that I am a nucleophile, that means I am plus loving. I'm plus loving, that means I'm having excess of electron. So if I'm having excess of electron, I'll try to move to that side of reactant where there will be deficiency of electron, which will be a plus. So in an organic reaction, there are two types of basic organic reactions, nucleophilic and electrophilic. Nucleo as in plus loving reactions and electro as in minus loving reactions. Now, once intermediates are formed, how these intermediates are stabilized? By electron displacement effects, which are basically of four types. Inductive, resonance and hyperconjugation are permanent effect. That is, if they are happening in a particular organic compound, they'll always be happening in that particular organic compound. But one is a temporary effect which is called an electromeric effect. Although you have inductomeric effect also, but for mains you can restrict your knowledge till here, that the temporary effect being electromeric effect, which is only applicable when an attacking species attacking a reactant, and that reactant is having pi cloud. We'll be discussing it separately. So starting with the very important electron displacement effect, and the very first permanent effect is inductive effect. Now, as the name suggests, inductive effect means induction. What is an induction? Let's say we have a carbon chain. Okay, every carbon is attached with another carbon. They have, both of the carbon members have equal electronegativity. No one is more electronegative, no one is less electronegative. So where will be the center of mass? Sir, this carbon has shared electron with this carbon. Both are carbon only, sp3 hybridized carbon. Neither this will try to be more electronegative, neither this will be try to be more electronegative. So where the center of mass of the bonded electron it will be a perfect sharing, so it will be direct at the center. No one is having illegal partnership over here. Everybody is a dedicated partner with 50% sharing, and therefore the center of mass of the bonded electrons will be just in between. Now, you already know through this in your inorganic chemistry, periodic table, chemical bonding. Now, if this carbon chain is attached with an electronegative atom, for example, let's say if it is attached with halogen. So we know halogens are very electronegative. They have very strong nucleus. What nucleus will do? Nucleus will try to grab electrons, to snatch electrons. Now, what is the orbital that is closest to the nucleus? Sir, s orbital. If s character increases, electronegativity increases. and s orbital makes what bond? They only form sigma bond. That's why inductive effect only deals with sigma electrons. Inductive effect never deals with pi electron. First important point that you have to always remember. Inductive effect only deals with sigma electrons. And obviously, because I'm more electronegative, so I will shift and try and play a tug of war with the carbon chain. And because I'm most strong, so I will be pulling the electron toward myself. Thereby, this center of mass between this carbon and the attached group, which is, let's say, halogen in this case, this center of mass will now not remain at the center, and let's say the center of mass of the electron cloud has shifted to halogen. Now, because I have taken some excess of electron towards me, I have not taken complete electron. If I would have taken complete electron, I would have attained complete -1 charge. But here I have attained a partial negative, and therefore this guy has, because this has taken electron, so minus, it has lost electron, so plus. Now look at this carbon and this carbon. Sir, if boss has said something bad to a father of a family, then this father, when will be going home, obviously the father will also be in frustration, but it will not take the frustration out in the family member. Let's say father has done some bad words to mother, but the intensity, let's say if somebody, if any person, any man, let's say outside of in a roadside, they have, so the man has a fight with some other person and received some punches. He will be getting some positivity. I mean, not that positivity, he must be getting some negativity, but he'll be attaining some charge, some bad emotions, some bad wounds. Once that person will be coming back, won't you think that he'll be also not be in that good state, so he'll be giving some of the bad things, bad words to the family person also? Yes. And once the family person gets scolded by the man of the family, then they will be giving some bad words to the children then, but the intensity will not be the same. What I'm saying is, if, let's say, for example, 100 coulomb of charge has been accumulated, for example, it is generally 10% happening to the chain. For example, if this is 100 coulomb, so this will be 10 coulomb charge and this will be 1 coulomb charge. Now think of in terms of money. If this guy has 100 rupees, this guy has 10 rupees, this guy has 1 rupees. Sir, here, because after 1 rupees you cannot find even a toffee. So actually inductive effect is also highly distance dependent and is operational till third carbon from where I'm attached. So if I'm creating charge over here, yes, it is additive effect, it will be prevailing in the whole chain, but it is mainly operational just to the group with which it is attached. But if at all theory is asking you inductive effect is operational till what carbon, then it is operational till 3 carbon. And because I'm attracting these electrons, so this group will be known as a -I group. Minus inductive effect. Obviously there will also be some groups which will be applying positive inductive effect, which will be dealing in the another slides. Now moving forward, just to summarize, what are the properties of inductive effect? When a covalent bond is formed between two atoms of different electronegativity, the person that is more electronegative will try to attract the bond electron towards itself, and such a shift of electron density result in the formation of a covalent bond that we know through inorganic chemistry. Now this shifting of sigma electron, that's why only sigma pi electrons we do not. This shifting of sigma electron density is known as induction, and due to this induction, adjacent atoms gets and develop a polarity, which we have seen. And this effect, this phenomena is termed as inductive effect. Now it is additive effect. For example, I have a carbon, I have that group here also, here also, here also. So I'll be having that effect 3 times. If I'm attached by just two of those groups, I'll be having it 2 times. So inductive effect is an additive effect. If you add, the effect will get added. If you subtract, it will get subtracted. Now, although it's a permanent effect, but it's a weak effect. Why? Because the later effects that you'll be seeing, electrons are not completely transferred. That halogen has not snatched the electron from carbon chain. The halogen has shifted the electron towards itself. So because there is no complete transfer of electron, therefore out of all these electron displacement effect, the very first effect, inductive effect, is the weakest. Remember this point, it is the weakest effect of all the effects that is coming after this, because here there is no complete transfer of electron, it is just shifting. This is highly distance dependent, and obviously as the distance increase, inductive effect was happening to the most extent in this carbon, and as distance is increasing, the inductive effect of this halogen is getting decreased. At the fourth carbon, it is becoming in fact 0. And this is written only 10% of the original charge transfer, and it actually becomes 0 at the fourth position. Moving forward. So quickly moving to the types of inductive groups. Obviously, there are of two types, plus I group and minus I group. But plus I and minus I, with respect to whom? As we have seen this carbon chain, so this reference IUPAC has chosen as hydrogen. So if this is hydrogen, it is R0. If there is a group which has the capability of winning that tug of war by withdrawing the electron cloud with respect to hydrogen, then that group becomes a minus I group. And if this group is losing the battle with respect to hydrogen and transferring its electron cloud towards the carbon chain, then it becomes a plus I group. So a plus I group is that which gives away its electron density, and minus I groups is a group which withdraw electron density towards itself with respect to the C bond H group. Now the main problem which students face is what are the types and how are they compared. Actually they are all experimental data, but I am giving you a trick to learn them. The most dominating plus I groups are those who have already got negative charge, because if I've got minus, more be the charge, more is the probability to give those electrons. So all the groups, if they already contain excess of electron, so they will be in a position to give away those electrons. So negatively charged species becomes the most dominating plus I groups, followed by alkyl groups, the carbon family, the carbon groups, and the least plus I group applying groups will be all those atoms. Although there are very less in number, you will not find them very frequently in JEE mains questions, but the minimum plus I group applying groups are all those atoms which are less electronegative than carbon. Talking about the minus I group, in the same way, the most dominating and strong minus I groups are all those species which already have a positive charge. So if I have a positive charge, I'll have more tendency to attract those sigma cloud also. So I'll be most strongly minus I applying group, followed by all the groups which have partial positive charge, and the last would be all those atoms which are electronegative than carbon, and you will find number of electronegative atoms. So in order to learn them quickly, what is the trick? Halogens are have strongest minus I, followed by oxygen bonded with another groups, followed by nitrogen species, and followed by the other hybridized carbons. Now sir, can you also throw some more light so that we can also do some questions quickly? Yes. Now I am giving you some very famous groups. This slide you have to learn. I mean, I have by observing many questions, I have made this, although most of the references also have this list, but that list is very more informative. So rather stick with this, will help you to do all your JEE mains question if it is asking you to apply and compare the strength of plus I and minus I group. Now coming to the minus I group, the remember the minus I, who apply the strongest minus I? All the positively charged species. So among them, NF3 with a positive charge, NR3, NH3. I marked them with green color. The second, the less dominating minus I groups were all the species which is having partial positive charge. So because of presence of two oxygen, this nitrogen will attain a delta positivity. There is no complete plus. Carbon, because of presence of triple bonded nitrogen, will also be highly electronegative. So partial positivity will make it very strong minus I group, but weaker with respect to NO2. And the CWH group, yes, you will find number of groups also, but these all are famous, which will make your question correct. Now the third section, halogens, fluorine, chlorine, bromine, iodine, they are the strongest, followed by oxygen species. So OR, then OH. Remember this, OR is strong minus I, then OH. This is an experimental data, you have to remember. Now after that, the nitrogen, I mean all the nitrogen groups like ammonia, like amine, NH2. Now some references will confuse you because they give this sp hybridized carbon first and this nitrogen later. That's why I've dotted that particular two sections. But for JEE mains, with the most of questions that they have asked, you stick with this plan, that halogens followed by oxygen followed by nitrogen and then the other hybridized carbon, that is sp hybridized carbon. We know it is having 50% s character, so it will be electronegative. So alkyne and then alkene. But among alkene and benzene, who is having strong minus I? Benzene. Because sir, only one alkene is playing tug of war, and over here three set of alkenes are playing tug of war. So obviously 3 will be withdrawing more electrons. So phenyl, and the least minus I group for us with respect to C bond H is an alkene. Now going to the order of plus I groups, all the negatively charged species. So CH2, NH2, O minus, and this O minus of the carboxylate ion will transfer the electron, and this carbonyl carbon will also transfer the electron to the carbon chain, and this carboxylate ion becomes a plus I group because it is having an excess of electron. Now you have to remember carbon is most electropositive among them. So if carbon is having an electron, so it will not have a tendency to hold it, so it will be most plus I, while NH minus, nitrogen is electronegative, although it is having electron, but obviously carbon having electron will be a better donor than nitrogen. So these are all species which are negatively charged and hence strong plus I groups, followed by the alkyl groups, which I guess we very well know. Most will be 3 degree, then 2 degree, then 1 degree, because 1 degree is supplied with the electron density only from one alkyl group, followed by as I told you, electropositive atoms. More electropositive atoms with respect to carbon are not very common in organic chemistry, but this isotopic effect, although not very famous in mains, but very famous for advanced questions, and mains have also few times asked them. Now what is this isotopic effect? Sir, we know this is just a methyl group. So methyl is just having C bond H and we are comparing with respect to H. So among CH3, CD3 and CT3, these D and T are just heavier isotopes of hydrogen. Hydrogen is having number of nucleons 1 because there is no neutron. Deuterium has 1 neutron, so its mass number is 2. And tritium has a mass number of 3. So the hydrogen is, the lightest of isotope, and tritium is the heavier version of hydrogen because nucleus is heavy because of presence of 2 neutrons. Now among them, CT3 among these 3, tritium version of CT3 is applying more plus I as compared to CH3. Now although you can learn it also, but for all those who want a common sense, you can think of like a string pulley system. Like, sir, this is heavier, So we in kinetic theory of gases, we also know that atoms have vibrational energy will be coming in between. So as per bond length, who is having the highest bond length, sir? It is very easy to predict, sir. C bond H bond length will be highest and C bond T bond length will be minimum. Now, if this bond length is minimum, think of it with a carbon chain. That means the electron density is more closer. That means this is having the electron cloud towards carbon chain, so it will be applying a more strong plus I effect. C bond T will be applying. This analogy we are making through the bond length. So C bond T will be having maximum plus I effect, while C bond H will be having the minimum plus I effect. This is an isotopic effect which you should know for good questions. Moving ahead, you can also learn it, but please do remember it. A very important concept which is I feel is very probable for JEE mains. Now, coming to the application, sir, we already have discussed the application where in the slide of smileys. Electron withdrawing group. If I am withdrawing electron, then who among inductive groups are electron withdrawing? The minus I groups. So minus I group are withdrawing electrons. So withdrawing electron will be favored to whom? Sir, carbanion is having excess of electron. So if someone is withdrawing electron, it will feel stable. So carbanion will get stabilized. So stability of carbanion, if I speak of stability of carbanion is they are stabilized by minus I group. So more be the minus I group, more is its stability. So it is directly proportional, and obviously it is inversely proportional to plus I, because if I'm already having electrons, so do not give me more burden. So it is inversely proportional to plus I group. Talking about over here, I'm taking carbocation and free radical for inductive groups. Now, as I've told you, for carbocation can be thought of as a free radical, not always, but yes. For talking of inductive groups, so stability of carbocation and free radical, because they are electron deficient, so they are stabilized by plus I group, and they are destabilized by minus I group, so inversely proportional. Talking about the acidic nature, sir, we very well know what is organic acids are weak acids. So let's say I have carboxylic acid, alcohol. They give H plus to a very small extent, but they will give some very less, but they will give some H plus and will form the conjugate base. Whatever will try to shift the equilibrium to right side will make this weak acid relatively more acidic. So if this conjugate base is stabilized, because this is having excess of electrons, so if this minus is shared by some group, so who all group withdraws electron? Minus I group. So minus I group stabilizes this conjugate base, while plus I group destabilizes this conjugate base, and therefore acidic nature is increased when minus I groups are attached, because in this case equilibrium will be shifting to forward direction. A very simple fact, and obviously it will be inversely proportional to plus I group. Talking of the application of inductive effect for deciding basic nature. So obviously, what is a base? Sir, base is a species which gives electron. So if I get some excess of electron from backside, that is I'm attached with some plus I groups, my basic nature will increase, because then I'll be having more electrons to give to the attacking species. So basic nature also becomes directly proportional to plus I group and obviously inversely proportional to minus I group. Now, taking this logic, if I compare ammonia and any alkyl amine, so ammonia is having no alkyl group. If alkyl groups are attached, then they will apply plus I, and because of application of plus I, this nitrogen will get more electron density of these lone pair, so it will be a stronger base. So alkyl amines are definitely a stronger base than ammonia. But if you want to compare the basic nature of alkyl amines, it is not governed by just one factor. Inductive effect we have already considered. So if you only see inductive effect, what you will say? 3-degree amines are strongest base and 1-degree amines are weakest base. But actually, where you will react? So reaction generally takes place in solvent, and the universal solvent is water. So actually, in order to decide among alkyl amines and ammonia, alkyl amines are always stronger base. But in order to decide the basic nature among alkyl amines, you have to consider 3 factors. One factor is definitely the most dominating is inductive effect only. But other dominating factors are, although less, are hydration and steric effect. Why I'm saying less? Because ammonia is a weaker base than any alkylamine. Because alkylamines, all alkylamines are definitely having an inductive effect. So this inductive effect is definitely most dominating. But this is not the only factor which decides the basic nature of amines. The other factors being the hydration and steric factor. Now what is hydration? Sir, I cannot react in gaseous phase. If you want to kick some person or hit some person, you actually have to be in a ground with that person. I cannot punch here and the other person receives punch. I'm in Madhya Pradesh, let's say other person is in Delhi. If I pick my hand up, can this hand hit the person in Delhi? No, I have to actually go to the same place. So similarly, where the reaction happens in solvent water. So first you get dissolved in water. First come to my home, come to my place. And what is the place? Every reaction takes place generally in water. So whatever amines undergoes solubility in water first will have the courtesy of actually getting reacted. First you come to my place, then you will try to react. And sir, organic compounds are not soluble in water, but with hydrogen bonding, they can very well be soluble. So which will be more soluble, which will be having more hydrogen bonding? Who has the capability to form hydrogen bond? N bond H. So 1 degree amine has 2 N bond H. 3 degree amine has no N bond H. So as per solubility of ability of forming hydrogen bond, 1 degree amine should be the most soluble. If I'm more soluble, I'll be coming to the system. If I'm coming to the solvent, I will be having, if I'm here, then only I will be having the opportunity to have that fight, though the person who has not even reached will have a less tendency of getting to any sort of reaction. So hydration says that 1 degree amine should be strongest base. Similarly, if I'm giving my electron, what electrons are transferred? The lone pair present on nitrogen. The lone pair on nitrogen is surrounded by only one alkyl group, so there is less crowding. But for 3 degree amine, it is surrounded by 3 alkyl groups, so there is much of crowding. And because of much of crowding, the attack of this lone pair can also get hampered. So steric effect also says that 1 degree amine should be the strongest base. So sir, then what will decide? What house is actually going to win will be decided by all the races. So the first race is the marathon race, which is having the highest point, the inductive effect, but there are other races also, hydration and steric race. So actually among alkylamines, who becomes the most base, strong base, is actually decided by the experimental value of equilibrium constant Kb. Sir, this Kb is what? This Kb is concentration of product upon reactant. So, sir, we have to learn the values. I'm just saying for alkylamines, the actual basic nature is an outcome of then this experimental data. You cannot blindly fold your eyes and say that you can decide who is a stronger amine. Inductive effect is the strongest. Why I'm saying that? Because all alkylamines are strong base than ammonia. Because ammonia has no alkyl group, so it loses the battle from all, and it is justified by mother nature also, by the experimental value of Kb also, we can say that. So sir, this is only we have to know. No, NCERT gives you one data. I'm not asking you to learn that data, but learn this trick. What is the trick? If you have methyl substituted amines, then the trick is 2, 1, 3, as in most basic are 2 degree amine followed by 1 degree, and the least basic are 3 degree amine. And if you have ethyl group as your amines, 1 degree, 2 degree, 3 degree amine, then again 2 degree amine wins the race, but the code is 231. Now methyl is a smaller group, so 2, because 2 never loses the battle. For inductive and for hydration and steric, you can watch 2 always has came in between. It has neither got the first place in any race, neither it has came last. So average performer, if you are studying 18 hours for some day and 1 hour on other days, then you are not a average performer. If someone is studying 10 hours every day, not 18, so I'm not winning sometime, even I'm not losing. I'm being a practical disciplined person, then this 2 degree is acting that like that disciplined person, that 1-2% of the people who actually get a seat in their IITs and NITs. So now the trick is methyl is smaller, so 2, 1, 3, 13 is smaller number, 31 is larger number. Why? Because ethyl is a larger group, so the extent of plus I of ethyl will be a bit larger. But we already know inductive is not the effect is just applicable for the very first atom. After the other atoms, the effect is just 10%. So, but still, because ethyl is more bulky, it can have a bit more plus I than methyl. Therefore, 3 degree wins the race from 1 degree. Trick is methyl is smaller, so 213. Ethyl is heavier, so 231. Moving forward. Now, discussing about some basic questions. Yeah, so as I was saying that this is a methyl group. Understood, sir. It will have plus I effect. Yes, sir. Let's say it is giving 100 rupees each. So 100 rupees by this, 100 by this, 100 by this. Yes, sir. What about this? Sir, this is giving 100 rupees because inductive effect is distance dependent. This is although giving only 10 rupees, but 100 plus 10 is actually 110. I'm not saying there's a very large difference, but I am giving 110, so 110, 110. So among these two, what will be the order of plus I? Sir, this will be showing a larger plus I, although not very large, but still larger. The methyl thing that I was telling you now. Again, some common sense. CH3 is having more plus I or SiH3. Sir, carbon is down the group. Carbon and silicon are same group elements, and down the group electronegativity decreases. So relatively carbon is more electronegative while silicon is with respect to carbon is electropositive. So this will be having a stronger plus I group. Now coming to the stability of carbocations and free radicals. So obviously I guess we have discussed this application. So directly applying this application with respect to the questions. So yeah. Can you tell me the stability of carbocation and free radical for inductive effect? You can obviously say conclude that carbocation is electron deficient and free radicals are also electron deficient. So for inductive effect, I am taking them as a group. So sir, this is doing what? Sir, this is a very strong plus I group. Sir, this is a plus I group, but this is having very strong plus I, this is having moderate than that one. And sir, this is a gone case because this is a minus I group. Minus I group destabilizes carbocation and free radical. So who will be more stable? This guy, and this guy will be least stable. Again, this sir we already seen that because of 3 alkyl groups, so there will be 3 plus I, so 3 degree carbocation will be most stable, 1 degree will be least stable. Inversely, if I'm having carbanion, then electron donating group will increase the burden on this carbon. So this will be least stable while, okay, I'm sorry. Among over here, there are 3 people who are forcing the plus I group. So plus I group destabilizes carbanion. So this becomes least stable and 1 degree becomes most stable. A very common examples, you will find number of questions applying this, asking you this logic. Now, what about this one? Sir, this is also a carbocation, this is also a carbocation. Understood. Sir, this is the point of difference. A methyl group, let's say after a distance of 1, 2, 3 carbons. Again, you have a methyl group, but after a distance of 1, 2 second carbon. So methyl group is a electron donating group, as in it is a plus I group. So if plus I group is relatively closer to me, the carbocation will feel more comfortable. So this is relatively closer, this is far apart. So this plus I is an electron donating group loved by carbocation. So this will be more stable. This is less stable because here it can't reach till this carbocation. While this reaches to a, maybe with respect to this one, it reaches to a larger extent, although we know inductive effect is quite distance dependent. So the impact will not be that much. And we have already discussed among all the electron displacement effect, inductive is the weakest because it is not completely giving it its electron. It is just shifting its electron. So, but because this is also weak, this is also weak, this weak is closer to me, this weak is far from me, so this will be more stable. Again, so for free radical also, this will be the scenario. And for carbanion, you are closer to me, you are away from me. I do not like either of you, but at least the person to whom I'm not liking is far from me. So this carbanion is more stable because electron donating group destabilizes. This is donating to a larger extent and that is donating to a lesser extent. So this carbanion will be feeling more stable. Moving forward, now the acidic nature for alcohol, for acid, all will form conjugate base. So who is stabilizing this conjugate base? This minus will be stabilized by electron withdrawing groups. So fluorine, yes, it is a minus I group. NO2, yes sir, it is also a minus I group. Fluorine, it is also minus I group. Okay, fluorine got tied, but among fluorine is a partial group. Fluorine is an electronegative just atom, and it is a group of made of electronegative atoms. So minus I of NO2 is strong. So this will stabilize this minus more. So most stable will be the second one, followed by this is also fluorine, this is also fluorine, so tie. But now distance will decide. This fluorine is from 1, 2 at third position, this is 1, 2 at second position, so this is closer, so it will stabilize to a larger extent. So after that, first is stable and the least stable will be the third one. Moving forward, now this is a carboxylic acid, H plus gone, a conjugate base is formed. So who will stabilize this conjugate base? Sir, similar question. Sir, apply minus. This will have a minus I effect. Yes, sp hybridized carbon. This is sp2 hybridized carbon. So this will be most stable, followed by this, and this is a gone case because this is plus I group, will be least stable among them. Therefore, this will be a strongest acid and that will be the weakest acid. Moving forward, sir, again, this is a conjugate base, although of alcohol. So connected with fluorine, connected with NO2, connected with Nr3. Sir, electronegative atom with a positive charge, strongest minus I. So it is strongest minus I. This is also minus I, but weaker. This is also minus I, but weakest with respect to these two. So this will be stabilizing to the largest extent, and this will be among the three, this will be the weakest conjugate base. So moving forward to delocalization of non-sigma electron cloud, that is pi or lone pair electron dealt by the second next electron displacement effect, which is resonance or mesomeric effect. Now, because sigma electrons were associated with shifting of electrons, hence it was the weakest electron displacement effect. And over here, the non-sigma electrons completely get transferred. Therefore, resonance becomes the strongest effect among electron displacement effects. Now, sir, we already know through chemical bonding that non-sigma electrons are present in unhybridized p orbitals. Unhybridized p orbitals can easily delocalize, and whenever there is delocalization of pi cloud, that is dealt under the name of resonance. But when that delocalization is happening under a system, what system? Under a traditional conjugate system, then all those delocalization of pi cloud are resonance only, but those delocalization are also termed as mesomerism, or the effect is termed as mesomeric effect. Now, sir, what are these conjugate systems? There are many types of conjugate systems, but the maximum number of conjugate systems of which you will find application in your JEE paper are these 5 types. Let us understand what this conjugate system is. When the non-sigma electrons are given a system of alternate positioning, for example, the very first example of traditional conjugate system is a pi sigma bonded with a pi cloud. For example, let's say I have this butadiene at 1, 2 and 3, 4 position. So definitely we can draw its structure, because through VSEPR theory we know every carbon over here will be a trigonal planar carbon. So this is lying in plane with this carbon. Because this bond is with the third carbon, so this third carbon also has to be in the same plane. So this complete molecule will be a planar molecule. We already know that these two must be forming that pi cloud. Similarly, these two must be forming that pi cloud, because the whole sigma bond is planar geometry. So there will be unhybridized orbital having sidewise overlapping. So can't you think of a scenario when this electron and this electron, like these two, sir, can also undergo, because pi electron is not directional. So if it is getting delocalized like this, it can also do like this. When it will do like that, even they can undergo overlapping and form the pi bond. Therefore, because pi electrons are free to move, when they are given a freedom of moving under a system called conjugate system, then this is resonance only. But this resonance is also termed as mesomerism. Now, first type of conjugate system is pi sigma pi. Next is pi sigma bonded with a positive charge. For example, this pi cloud is sigma bonded with a positive charge of carbon. Next is pi sigma bond minus. Next is pi sigma radical. Next is pi sigma lone pair. Now, obviously, what does pi represent? A non-sigma cloud, sigma bonded with a non-sigma cloud. That's why I said you will find more conjugate systems, but logic will be same. A non-sigma cloud, sigma bonded with a non-sigma cloud, so that they are free to delocalize. And this delocalization is also termed as mesomerism. Now, one question that will be coming to your mind, sir, that this lone pair can go here also, because it is not a sigma cloud, and this pi cloud can also go here. Sir, so what transfer or what delocalization will be dominant? All this will be decided by the rules. Once the non-sigma electrons gets delocalized, various resonating structures or canonical forms are produced. All these resonating structures do not exist in nature. They are just a theory. But that theory give rise to a resonance hybrid, as we have already discussed in chemical bonding, but I'm iterating it again. And that resonance hybrid actually exists in nature. And to that resonance hybrid, how do you make that resonance hybrid? By the canonical forms. And which canonical form will be contributing mostly to that resonance hybrid? For example, the molecule always exists in the form of the average resonance hybrid that you have formed. If you make 100 reactions of that molecule, then the molecule will be reacting as per that canonical form to the maximum number of times, which is more stable. So deciding the stability of resonating structure again now becomes the most important thing. So discussing about the stability of resonating structures. Now, remember one thing, apply these rules sequentially and try to remember that what rule has came first. Now, the many references gives many theory around it, but this is a concise rules that I'm giving you, which will be, I've limited all those rules, but you have to learn them sequentially. So first, what you will see among resonating structures, first you will see that octet of second period elements must be complete. If it is not, then that particular resonating structure is unstable. For example, let's say this is one of the resonating structures. Sir, we very well know, because we know electron move from higher concentration towards lower concentration. Here there is a vacant orbital, therefore a positivity. Here there is excess of electron. So, sir, now this is also untraditional conjugate system for you. Why? Sir, it is plus sigma bond lone pair. So this was not a type of conjugate system that we just read. So that's why I said you must be a non-sigma cloud must be sigma bonded with a non-sigma cloud, so that delocalization can take place. So that also becomes a conjugate system. Now, how will you think, sir, electron always flow from high concentration to low concentration? So let us do that. So these lone pair will try to move here. Definitely yes, sir. I'll just change the color. These lone pair will try to move here. Okay. So once they move here, let's say this electron and this electron. One electron has left atomic structure of oxygen. One is still there, but still oxygen will make a bond. So this lone pair has become a pi bond. Because carbon has received this electron, so the positivity is gone and the positivity came to this oxygen. Now, what many of the students do is, among these two resonating structures, which is more stable? In order to decide stability, the very first rule is first check the octet of second period elements. Here octet of carbon is not complete. Here octet of carbon is also complete. Oxygen is having 6 electrons in its outermost shell. It is having a positive charge, so 1 gone. So how many electrons are left? 5. But how many bonds this oxygen is making? 3. So 5 and 3 is 8. I'm sorry. So 5 and 3 becomes 8. That means octet of oxygen is complete and carbon is also complete. What people do is they start looking at the charge. What is the first rule? Octet. If octet of all elements are complete, then that particular resonating structure is always stable no matter what. We have not even reached to, because the octet has decided as the stability. So which is more stable? Sir, here octet is complete. So 2, second resonating structure becomes more stable than the first one. Now, will this molecule exist as this form or this form? No. In nature, when we have gone, or else if we see just this structure, or let's say we see this structure, we'll say that this bond is bond order 2. No. It will be single also, it will be double also. So in resonating structures, what remains in the same place where they are? Nucleus and sigma cloud never moves. What moves? The non-sigma cloud. So that's why for average resonance hybrid, I have made the nucleuses and sigma cloud as it is. What will be delocalizing? The pi cloud. So this can be single also, this can be double also. So instead what we should do is a partial double bond between carbon and oxygen. Sir, what about the charge? The molecule will be carrying the charge as a unit. So this whole molecule will be carrying that positive charge. But to this resonance hybrid, how will it be reacting to a larger extent with respect to this resonating structure? Because this will contribute more towards the resonance hybrid. Now, coming to the second rule for stability, which is always after checking the octet, neutral structures will be more stable than the ionic structures. And obviously some references write more be the number of covalent bonds. Neutral structures will definitely be formed when number of covalent bonds will be higher. So what we are learning is, second rule is, neutral structures are more stable than the charged or ionic structures. For example, sir, this is structure number 1, a neutral structure. But sir, we can see conjugate system. How? Pi sigma lone pair. Now, because I see excess of electron over here, so what we should think of making the first resonating structure is this one. So this lone pair forming a pi cloud. Oxygen lost 1 electron through it to its atomic structure. 1 electron is gone, so it attains a positive charge. And this carbon, once this carbon has received an electron, this pi cloud will be transferred to the first carbon. So it will be attaining a negative charge. Now, this is a neutral molecule while this is a charged molecule. So among these two, okay, first, what will be the resonance hybrid? So this is double, this is single. Here this is single, this is double. So there will be a partial double bond character. And overall, there's no charge, so I'm not putting any charge. So this attain a partial double bond character. And when we have gone to Mother Nature, we have seen also that this was not an exact double bonded carbon. As per bond length, we can check also. The bond length of this C bond O will not be that of a single bonded C bond O. It will be lesser because bond order is increased because of partial double bond character. So bond length will be reduced. So all those chemical bonding concepts will also be applicable. But here first, so this becomes the resonance hybrid. And now let's discuss about the stability. So we very well know, sir, this is more stable than this one because that one is neutral. So one becomes more stable than second because obviously you can see octet of all the elements are still complete. Moving ahead. Now, the third rule is negative charge on more electronegative atom and positive charge on less electronegative atom is more stable. Now, let's say I have this structure. Okay, what resonating structure I can predict? Sir, minus sigma bond pi, electron will move from higher concentration towards lower concentration. So this pi will be gained by this oxygen. So where we have reached, sir, this minus has recently formed a pi cloud and oxygen has gained the extra electron. Now over here negative charge is on oxygen. Over here, negative charge is on carbon. Negative charge on more electronegative atom is more stable. So because oxygen is more electronegative, so structure 2 will be more stable than 1. What will be the average resonance hybrid? It will be a partial double bond. It will be a partial double bond, and the whole molecule will be carrying this negative charge. To this resonance hybrid, which structure this compound will be reacting more, number of reactions given will be more with respect to which structure? With respect to this structure, as an oxygen will be giving out electron, because that resonance hybrid which is more stable will contribute more to the resonance hybrid, and resonance hybrid is the actual structure by which the molecule is supposed to react in nature. Now again, moving to the next rule, the fourth rule is, when there are equivalent forms, like you are forming resonating structures and let's say you find that both structures are equivalent. For example, let's say this is a carboxylate ion. Carboxylic acid, when loses H plus, forms carboxylate ion, RC double bond O minus. Sir, this is excess of electron, so pi sigma minus, a conjugate system. Electron will flow from higher concentration towards lower concentration. So this becomes minus and a new pi bond is formed over here. What about the resonance hybrid? This can also be double, this can also be double, and the whole molecule carries the negative charge. But if you apply rules in these two structures, you will end up saying that both structures are same. So when any species has equivalent resonating structure, then resonance stabilization becomes maximum. That is the reason when you say, let's say benzoic acid and phenol, if you, we'll be drawing it, if you draw phenol, you can draw various number of resonating structures, 5 resonating structures. But for benzoic acid, for the RC minus, you can only draw 2. For RC minus, you can only draw 2. So still we say that carboxylic acid are stronger acids than phenol, although phenol have more number of resonating structures, because number of resonating structures, more be the resonating structures, more be the stability. But more be the resonating structure, more is the stability. Does I have written that rule? No. So in the priority, what rule has came to fourth position? That is, equivalent structures are more stable and they give lot of resonance stabilization through the molecule. Now, so that's why carboxylic acid are always, any type of carboxylic acid, even formic acid, even methanoic acid, is a stronger acid than aromatic alcohol called phenols. Phenol although have 5 resonating structures, but still carboxylic acids are strong acids, because aliphatic carboxylic acid can form what, 2 resonating structures, but all these resonating structures are equivalent, and equivalent resonating structures gives maximum resonance stabilization. Moving forward, the next rule is resonating structures having closer distance between opposite charges, because plus minus attract each other. So if plus minus is closer to each other, it will be more stable. Similarly, I've not written that rule because that becomes an obvious analogy that similar charges should be far apart. But what you find maximum number of cases is, if you have 2 resonating structures like these two, here plus minus are far apart, here plus and minus are at closer distance. So structure number 2 will be more stable than structure number 1. Moving forward. Now, although I can write many more rules, but these are the rules which will be more than sufficient for you. Now, because equivalent structures give more stabilization, and we know benzene have got only 2 resonating structures and all are equivalent, that's why we get a circle in benzene, which shows the partial double bond character. Now, while looking at benzene, it has got resonance stabilization, but it has got extreme level of resonance stabilization. When scientists found, they named that extreme level of resonance stabilization. Resonance is a stabilizing effect. But what is extreme case of resonance stabilization? Some compounds have got that extreme case of resonance stabilization through experiments we have observed, and after doing that experiment we have devoted, I'll be coming back to it, but first let me discuss about aromaticity. So what scientists did name to that extreme level of resonance stabilization is they called those compounds aromatic. So after learning resonance, let us define what are aromatic compound. Only benzene is not an aromatic compound. Benzene is having that maximum stabilization which other compounds are also having. So whatever compounds are having that extreme case of resonance stabilization are called aromatic. And what is its definition? It's a 3-step definition. If you want to become aromatic, then first you should have a cyclic geometry. Although till 7-member carbon chains can come in a cycle. If someone asks you if they do not have any pi cloud, because pi cloud will be helping you to get this resonance stabilization. So let's say if you just have a cycloalkane is free to move in nature. The conformational isomer can be formed. So cyclohexane is not a cyclic molecule. But when a cyclic molecule having that pi cloud receives the maximum stabilization, then all the carbon can align themselves in a single plane. Because if you are a molecule and if you are given some good perks, then you will be staying in that city. Like you do a job, you will be doing a job in any city where you will be getting paid to a larger extent. Similarly, carbons, if someone is asking you cyclohexane is planar, is always planar. No. Cyclohexane is not a planar molecule, but 7-membered carbon ring or 7-membered ring can come to a plane if they get some perk. And what perk? Of having the maximum stabilization. So yes, if you get a cyclic conjugation of non-sigma cloud, then cyclic structures can be planar, but till what? Till 7-member ring. Remember this, because if you have 8-member ring, because of so much of crowding of 8 members, a 8-member ring cannot come to a single plane. So this aromatic definition is valid only till 7-membered ring structure, because 7-membered ring structure can come in a plane. And the first condition for you to be aromatic is you should be cyclic and planar. Second is definitely you should have complete delocalization of that pi cloud, as in pi, sigma, pi, whatever conjugate system we have seen, they should be alternatively present so that a cycle, a current loop must be formed. Because now these pi electrons will be delocalized in itself only, and hence they will not react to the outside world. And if I'm not reacting, that means I'm stable. So first is you should be cyclic and planar. Second is you should have a complete current loop of those pi clouds. And third is how many pi electrons should be responsible for forming that current loop. It should be 4n plus 2 pi electron. N can be any whole number. Let's say if n is 0, so 2 pi electron can do that, 6 pi electron can do that, 10 pi electron can do that, so on and so forth. You can keep increasing n by 1, but these are all the basic cases which you will find in your paper. Now all these 3 rules are termed as Huckel's rule, because Huckel has extracted all those stable compounds in nature and found these properties in them. Now also while doing experiment, scientists observe that if you satisfy the first 2 conditions, that's why I've made 2 ticks, the current loop is also there. If you have got this much of pi cloud, that means your nature is diamagnetic. But if you get 4n pi electrons making that current loop, then you satisfy first condition also, second condition also, and if you satisfy third condition but you are only falling short by 2 electrons, if that current loop is formed by 4n pi electrons, then those particular compounds were not found to be stable. They were found to be very reactive. Sir, if I'm very reactive, that means I'm very unstable. Yes. And sir, what are in all other cases? If someone satisfies this but not this, this but not this, in all other cases you are a normal average person. You are a mediocre. So aromatic compounds are topper. Everybody wants to be a topper. You have done everything correct in your life. You were just going to get AIR1, but suddenly you didn't get even was not able to complete engineering only. Have you seen Pan Singh Tobar? Yes. A very efficient guy, when loses, becomes anti-national. I'm not saying otherwise, but just for the case you should understand that aromatic compound are stable. And when I have satisfied the first two conditions, and third conditions also I satisfy, I was just falling short of 2 electrons. So I worked so hard, but I didn't get it. And that condition is condition of being an anti-aromatic compound. And anti-aromatic compound are not stable. They are not less stable, they are actually unstable. So if a molecule is becoming an anti-aromatic compound, it will never try to go in that direction where anti-aromaticity is attained, because this is not stability, this is actually the unstability. This is actually a synonym of instability. And in all other cases, you will be an average person, a mediocre, a normal person. So non-aromatic compounds are less stable. Obviously, they are normal compounds or normal intermediates. Aromatic compounds are stable. So stable intermediates, and stable intermediates will be formed. Now, remember one thing. As we said, reactants getting formed into a product, you always have to climb up to an activation energy high. That activation energy high can only be climbed by those intermediates which are stable. Now, for intermediates, do not apply that thermodynamic rule that if I'm stable, I will not react. Who all intermediates are stable, they will be formed, because for intermediates, they have to be formed for a fraction of seconds. So intermediates are like terrorist people. Just for example, intermediates are like terrorist guys. A terrorist, like the Mumbai attack which have taken place, the terrorists that have came to Mumbai, they must be out of those 100 and lack of they must be having at least some set of people who they can send. Those 6 must have been got selected. So intermediates are like those terrorists, that they were the stable among those people who are going to die. Who are going to die, as in intermediates will definitely react and will form the product. But that intermediate will be formed which is more stable. So for intermediates, whoever is more stable will climb the activation energy barrier. Because why it is climbing the activation energy barrier? Because among all intermediate, it is stable. So stable intermediates are formed also, but they are reactive also, because they will only be reacting and forming the product. So if any intermediate is attaining aromatic nature, it will be formed and it will be very stable. Very stable as in it will be formed and then it will be turning out to be forming the most probable product. So aromatic compound are most stable, followed by non-aromatic, and least stable is anti-aromatic, which is having 4n pi electron cloud forming that current loop. We'll be doing some examples now. Coming to this, because now we know aromaticity also. So summarizing what resonance we have read till now. So sir, resonance is a permanent effect like inductive, but it is the strongest one. It takes place within the molecule, obviously, so it's intramolecular. It has no effect of distance, so it is distance independent. Inductive was highly distance dependent, but a pi cloud can move anywhere because it takes after successive sigma bonds, if you position pi cloud, so 1 pi electron can even reach from this place to n number of places. Why? Through alternate crowding, because nucleus is not moving, pi cloud is moving. So it is distance, it is independent of distance. Now resonating structures, all those resonating structures, like you have, let's say, 4 resonating structure for a compound, so they exist in nature? No. So resonating structures are hypothetical, they do not exist in nature. What exists in nature? Through the resonating structures we predict a hybrid, and that hybrid is actually real. It represents the molecule, and generally the most stable resonating form contribute more to the resonance hybrid, but that resonance hybrid is having the minimum energy, as I've shown you with this graph. That let's say I have 4 resonating structures, out of which who is most stable resonating structure? The first one. Why? Because it is having least energy. But that resonance hybrid is not this one also. It will be a contribution of all these 4, and that resonance hybrid energy will be lesser than even from the most stable canonical form. So energy of resonance hybrid will be somewhere around here, for example, and the difference between the energy of that resonance hybrid and most stable canonical form, that difference is actually termed as resonance energy. calculation of resonance energy questions are mostly famous for advanced, but also I've included this topic also. Now, moving forward to discussion of some aromatic compounds. So this JEE Mains 2023 question says that compound A is a reactant with two equivalent of bases. What does a base want? A base want H plus. So these H plus will be removed in form of water and O minuses will be formed, which will be our B. So let us draw that B. This is a double bonded O, this is a double bonded O, there is a pi cloud, this is O minus, this is O minus. Now this is our compound B. Now we have to check that whether B is aromatic or not. Without even drawing the resonating structures, you can say, sir, pi sigma, this minus will be going over, so you can get a plus over here, you can get even a plus over here. So pi sigma plus sigma pi. So obviously I can see there is a cyclic conjugation, but because this is the first question we are attempting, so let us draw those resonating structures also. That's why I've drawn this picture for you. So once this latest O minus has formed, let us delocalize it and check whether it is forming a cycle or not. Like in case of benzene, it is formed. So this cloud can very well go till here. This O minus resonance is not distance dependent. So that O minus is reaching here. So let us draw that structure. This single bonded has just now become a double bond O. This pi has been transferred over here and this has become a O minus. Rest are as it is. So this is again a O minus as it is, and this is a double bonded O. So I can find two double bond O and two O minuses. Now, further, sir, this pi can be reaching here also. How? Let us change the color and check. This electron flows from higher concentration towards lower concentration. Once this electron is coming over, this pi cloud will move this side, and this pi cloud will be attained by this O. This O will again become O minus. This has recently changed to double bonded O. Rest are as it is. So this is O minus only, and this is a double bonded oxygen. Further, yes sir, still because I have, okay. What I missed is this pi. Okay, so I'm sorry. Now, this pi should go there also. Let us check whether it can go. So again, the delocalization of pi cloud, obviously, I guess it is quite clear to you. This is a double bonded O. Remaining bonds are as it is. And pi has recently reached over here. Now, once again the delocalization takes place, what happens is this minus come over here, this pi cloud over here, this over here. I guess you will be reaching to your initial structure. So, sir, pi cloud is delocalizing in complete ring. Although you can, without drawing, you can also say, but because this is the first aromatic question we are doing, so condition 1, it is cyclic and planar. Condition 2, complete delocalization, so a current loop is forming. And condition 3, how many pi electrons are forming this loop? Although there are many pi electrons, but that delocalization, that circle is formed by how many? By, sir, only these 2 electrons. So how many electrons are forming this circular loop? 2 pi electrons. So Huckel's rule is followed. So definitely B is a cyclic, B is an aromatic compound. Statement 1 is correct. The completion of above reaction is very slow, as we have already discussed. Sir, any reaction proceeds here, an aromatic compound is formed. So if this is an average, this is a cyclic structure, but in this structure you cannot find cyclic conjugation, so it's a non-aromatic compound. An average person, you are asked to become AIR1, won't you say yes? You will definitely, you will be gone crazy. So this reaction will be crazily happening in forward direction, so it will be very fast. It is saying it's a slow reaction, so this is wrong. A, now this shows tautomerism. Now this compound is not having cyclic conjugation, so it is a normal compound and a non-aromatic compound. So it can show tautomerism. How? This is double bonded carbon with OH, so it's an enol form. This beautiful hydrogen, I mean any of these 2 hydrogens, this double bond can come over here and this hydrogen will be gone over there. So let's say it is the enol form. So its keto form will be, you will be having this cyclic chain, double bonded O, this is an OH. Recently, this has become a double bond O, and that extra H would be reaching to this place. So this is your keto form. Yes, sir. Because it's a normal compound. It is also a normal non-aromatic. Non-aromatic are average normal compounds. So I was normal there also, I am normal here also, although keto form will be more stable than this enol form. Okay, keto form, this keto form will be more stable, but because we know it can form aromatic compound also, this will also be in competition. But as far as whether it can form tautomer or not, yes, it can definitely form a tautomer if it is in state A. So yes, it can show tautomerism. The bond length of CC in compound B. Compound B is aromatic, so how you write benzene? You draw a circle. So over here also what key we can draw is the average resonance hybrid will be, every bond can be a double bond. So every bond will have a partial double bond character. So bond length of all C bond C will be equal. Moving forward. Now, this mains 2024 question says you have to tell what are the number of, so it must be an integer type question, number of aromatic compounds. Obviously, this first structure I can see an sp3 hybridized carbon. So sp3 hybridized carbon is tetrahedral. The first condition for being aromatic is you have to be cyclic and planar. So an sp2 hybridized carbon is trigonal planar. sp3 is not even planar. So because I find sp3 hybridized carbon, so this becomes a non-aromatic compounds. Let us move here. I can also see sp3 hybridized carbon. So this after delocalization also, that I mean this pi cloud can move there. But in order to move there, it needs an sp2 hybridized, some orbitals it needs which are unhybridized. So sp3 hybridized system can never show cyclic conjugation. So this becomes also non-aromatic. Now, normal compounds. What about this? Yes, sir, it is cyclic conjugation, pi sigma plus sigma pi, sir, it is having cyclic conjugation also. And how many electrons are creating this conjugation? Oh sir, 4 pi electrons. That means it has just fallen short of 2 electrons because of that positivity conjugation. Cyclic conjugation is there, but this cyclic conjugation is created by 4 pi electrons, so it becomes an anti-aromatic compound. Very bad. So we were as aromatic, so not an answer. Now, this is a 8-membered carbon chain. 8-membered carbon chain, as I've told you, because of crowding, even if it attains aromaticity, still it cannot show, I mean, even it contains cyclic conjugation, like over here it is containing cyclic conjugation, but 8 members can't even come in a plane. So it can never be an 8-membered ring, can never form an aromatic compound. So this will also be a non-aromatic compound, because even it is not cyclic, it is not anti-aromatic also. Because in order to be anti-aromatic, you have to be cyclic and planar. It is not even cyclic, so it is not anti-aromatic, it is a non-aromatic compound. Although this much question is not asking, it is just asking you the number of aromatic compounds. So till now we have got no aromatic compound. Now obviously this is a 6-membered ring. 6-membered ring, although 1 member is nitrogen, but 7-membered ring can come in a plane. So this can come in a plane. I can definitely find cyclic conjugation of pi sigma pi sigma pi sigma pi. Now there is a nitrogen. These lone pair of nitrogens are not even allowed, they are not invited to play in the family in the cyclic conjugation. There is an existence of nitrogen lone pair. Just go to VSEPR theory. How many sigma bonds nitrogen are forming? 2. How many lone pair it is having? 1. So its hybridization will be sp2. Shape will be a bend shape molecule. So this is a bend shape molecule, and this lone pair will be oriented this side. It will not be perpendicular to the ring, because perpendicular lobes are supposed to delocalize. So this lone pair is not even allowed, is not invited in the delocalization. It has lone pair of electrons, but it is not invited. It is not participating in cyclization. So Huckel rule says how many cyclic loop is formed by what number of electrons? 4n plus 2 pi electrons, which is formed by 6 pi electron. There is a presence of lone pair, but it is not participating. A very beautiful example of pyridine. Because these lone pair are not at all involved in hybridization, in aromaticity, therefore it is also a good base also. This lone pair can be donated also, because they are not invited in being the more stable aromatic ring. So how many pi electrons are forming this aromatic ring? 6 pi electrons. So yes, this deserves the definition of being called a aromatic compound. The last one, I can see an sp3 hybridized system, so it cannot even form, it's not even planar. So how many aromatic compounds we have? Just one. Moving forward, among the given aromatic compounds, the total, these all are JEE mains questions, so pay huge amount of attention over here. The total number of, again you have to tell the total number of aromatic compounds. It will be an integer type question. So sir, I can see sp3 hybridized system. So because sp3, it is a non-aromatic compound. What about this? So this is a benzene. Now benzene and its derivatives. If I am a benzene, I am showing the property of an aromatic compound. You connect whatever with me, but I am following the definition. So these are derivative of benzene, aromatic compound. So because of presence of benzene, this whole compound becomes a family of aromatic compounds. So yes, this is an aromatic compound. I have to tell number. So this is first aromatic compound. Second one, again, there is a minus charge, although with this ring also you can check that it is aromatic, but still, because I can make benzene also, and I want you also to pay attention to delocalizations as well. For example, let's say this minus is delocalizing over here. If this minus reaches over, this pi electron is kicked, it will reach over there, this pi electron will reach over here, this pi electron will reach over here. As soon as this electron is approaching here, this electron will be taken by this carbon. So minus will be coming over here, a pi bond over here, and pi. This will now become a benzene, and therefore it will have a derivative. So it is also benzenoid. With this structure also I can say it is aromatic because it is cyclic. Point number one, planar and complete conjugation, and it is the complete conjugation is by 6 pi electrons. So following Huckel's rule, so this is also aromatic, but you can see this side is forming benzene also. Now the last one, again, it's a benzene and its derivative, although this ring is also aromatic, this ring is also aromatic, and when we consider this ring, there are also presence of 6 pi electron. So all the three rings themselves are also aromatic. So obviously, even if this would have been there, then only I would have given it an aromatic compound, because benzene derivatives are also aromatic compounds. So how many aromatic compounds I have? 3. Moving forward, very simple questions, but you should know the definition by heart. Now next question is, among the following the aromatic compounds. Okay, the same question. Among the following, who on options are given, who all are aromatic? So let us point, sir, this is an sp3, so this becomes a non-aromatic compound. Option 1 gone. This is benzene, definitely an aromatic compound. Cyclic, yes. Planar, yes. Complete cyclic current loop, pi sigma minus sigma pi. So yes, a cyclic loop, current loop of pi electron is also there. And how many pi electron you see? 6 pi electrons. So it is definitely aromatic. What about this? Cyclic planar, condition 1, yes. Condition 2, complete delocalization, yes. Pi sigma plus sigma pi sigma pi. So a cyclic loop is created, but created by how many electrons? I guess now it is quite clear to you. JEE asks it number of times. The cyclic loop is created by 4 pi electrons. So it becomes an anti-aromatic compound. So not an answer for us. So how many are aromatic? Second and third. Second and third. D. Now, among the following compound, again, now you have to tell which is not aromatic. This not thing, always pay attention to. People miss it out of curiosity and hurriness. Now, cyclic planar. So first point, sustained. Second point, it should have cyclic delocalization, so alternate position of conjugate system. Pi sigma plus sigma pi, second tick also, I mean the second condition also. Now it should be cyclic conjugation, cyclic loop should be formed by 4n plus 2 pi electron. So how many pi electrons are there? 2 pi electrons. So third tick also. So this is aromatic. Perfect. Now what about this? Tick 1, yes, it is cyclic and planar. Tick 2, yet yes, it is forming a loop, pi sigma plus sigma pi, but again the same question, 4 pi electrons are doing that, so it is an anti-aromatic compound. So not an option for us. It is anti-aromatic, actually an option for us, because question is asking which are not aromatic. So this is not aromatic, and what? It is an anti-aromatic. So actually this is not an option for us. While this is right, we have to check aromatic. So which we have to check which all are not aromatic. So it's an anti-aromatic compound, so not aromatic. Now what about this one? Tick 1, yes, because it is 7-membered ring. Tick 2, yes, I can see a cyclic pi loop of pi electrons. Third, let us check the electrons. 2, 4, 6, and there is a minus. So it's 8 pi electrons. So again, it is an anti-aromatic compound. So anti-aromatic is not an aromatic. So yes, an answer for us. Now, last one, fourth one. No, this is having an sp3 hybridized carbon. So this is also not aromatic, but this is not anti-aromatic. This is non-aromatic. Although question is not asking you, but this you will take this also as your answer, because question is asking which is not aromatic. So non-aromatic and anti-aromatic, both are not aromatic. So our answer is 2, 3 and 4. 2, 3 and 4, option A. Moving ahead. Now the aromaticity definition you can also apply with reaction intermediate stability. So these all are carbanions. Question is asking you arrange them in order of stability. So let us find the resonance provides stability, but aromaticity provide extreme level of stability. So let us check who all are aromatic. So obviously we have seen so many examples. Cyclic, complete cycle of pi cloud, and how many electrons are making that pi cloud? 6 pi electrons. So this is definitely aromatic, and because it is aromatic, it will be most stable. So fourth will be most stable. Which option A gone, option B gone. Fourth is most stable, fourth is most stable. Now let us check the least stable first and second. Obviously I can see this is condition 1, satisfied cyclic. Condition 2, yes sir, delocalization, cyclic current loop. And condition 3, 1, 2, because there's a minus, so there's be two electrons, so there are 4 pi electron, but this makes it an anti-aromatic compound. Aromatic you want to form. If somebody is asking you, you do all the labor and you become a terrorist, you will not go that side. So anti-aromatic is not stable, it is not unstable, it is very unstable. So this will never be formed and hence will be least stable. So our answer is D. Although we got our answer, but out of 2 and 3, question is telling you 3 is stable. So why 3 is stable? It is also a 2-degree carbanion. It is also a 2-degree carbanion. No resonance. Inductive is also same. So remember in GOC-1, while isomerism we said, when compound undergoes cyclization, a pair, they are forced to, the bond angle of 109 degrees forced to come closer to each other. So they are at strain. Which ring is free from any type of strain? 6-membered. 5-membered has some strain, but although very less. And 4-membered, if you keep on decreasing the carbon chain, bare strain will increase. Hence 3-membered ring structure is very unstable. 4th is also very unstable. 5th is okay. 6th is free from every type of strain. So but 4 will be having more strain than 5. So 5th, this will be more stable than 3rd, will be more stable than 2nd because of Bayer's strain. Although this is not asked in the question, but still giving you so that you know all the logics. Moving forward, this brings us to types of resonance effect. Now, just like inductive effect, resonance are also of 2 types: electron donating groups or electron withdrawing groups. So plus R or plus M groups are those when the conjugate system is attached with an atom and that atom is actually containing lone pair of electrons or some negative charge, that is, there is a formal charge which that atom has attained, and therefore because excess of electron will definitely try to flow. So if I have excess of non-sigma electrons, they will also try to flow. So whenever a groups, like for example, the famous example of conjugate system is a benzene ring, the pi sigma pi cloud. And JEE also loves asking that pi conjugated system of benzene when attached with different groups makes it a substituted benzene. So whenever these atoms like nitrogen having lone pair of electrons will definitely donate these lone pair of electrons to the benzene ring, so it will behave as an electron donating group. But by what? Due to a resonance effect, and because there is complete transfer of electrons, so it will definitely be a very strong electron donating group than a simple plus I group. Other examples like this nitrogen alkyl substituted amines, alcohols, ethers. Carbon does not have electron, but anion, if carbon is having an extra electron, that can also flow into the conjugate system. O minus also applies strong, plus I also applies strong, very strong plus R as well. Even halogens, although they are electronegative, but that electronegativity deals with the transfer of sigma electrons. So fluorine, chlorine, all these halogens, although we'll be discussing much about them in alkyl and aryl halides, but one thing I'm telling you here only, these fluorine and chlorine, although they apply plus R, so they give electron density via resonance, but because of their highly electronegative nature, they apply strong minus I as well, and therefore they are having a mixed effect on benzene ring, because they are on one side giving electron from their plus R nature, but because of their strong electronegativity, they have strong minus I as well. This is about fluorine, sir, but what about halogens? The other halogens and actually all those atoms which have lone pair can donate that lone pair. But if they have vacant orbital, then because of the presence of that vacant orbital, they even have a reverse effect. That is, they can even withdraw the pi electron density. So this chlorine can act as both plus R group also and minus R group also. I am not trying to make things complex for you, because in alkyl and aryl halides and in few questions we'll be seeing that if someone is asking you at first place what type of group this chlorine is, so it is definitely an example of plus R group, so I've written it over here. Now what about this, sir? Why this amide and this ester, oxygen and nitrogen, if they are directly connected with benzene ring, sir, they have lone pair, so they have lone pair, so they will donate. But you can definitely see they can donate these cloud to the conjugate system, but they are in cross conjugation. There is a presence of a strong electron withdrawing group, the carbonyl group, so even resonance can take place this side also. So they can, obviously they will have a plus R effect over there, but they can also have plus R effect over here. So this will be a cross conjugation, so their plus R nature will be decreasing to the benzene ring, because they are also having a demand of getting electron from this carbonyl side, and so is the case with ester. It will be a plus R group for the attached conjugate system, but it can, because of the presence of cross conjugation, it also has to furnish these electrons to the other side. So these groups will have plus R, but their extent of plus R will be much lesser because they are in cross conjugation. But an example of plus R groups. Now what are minus R groups? Or as I already said, for carbonyl group, this COO group. Sir, whenever an atom is attached to a conjugate system and it has vacant orbital, so those vacant orbitals, vacant orbital is deficiency of electrons. So that deficiency of electron and couple up with, if it has a positive charge, as in that orbital is vacant, will make it a vacant orbital which is demanding electrons. So obviously it will demand electron from the conjugate system and will become a minus R group. For example, all the carbonyl groups. So in general you can always say that if carbonyl group is directly attached with a conjugate system, whatever it may further be connected with, if it is an hydrogen, it's an aldehyde, ketone, aromatic ketone, if there is an OH, it is an carboxylic acid, even carboxylate ion, COO minus, with that O minus you will see, sir, it is minus, it will give electron. That O minus is not getting connected with the conjugate system. Actually this carbonyl group is only connected with the conjugate system, so this will definitely demand electron, because this oxygen will always withdraw electron from carbon thereby making it minus and creating a positive. A complete empty p orbital of carbon will always make this carbonyl carbon highly electron deficient, and it will always acting as a minus R group. So similarly, carboxylic acid and its derivatives, all these will be example of minus R group. Now one more. Nitrogen, sir, but there is no vacant orbital in nitrogen. So, carbon also didn't have that, but it is created due to the attached electronegative oxygen. So over there also, the attached electronegative oxygen will create a vacant orbital, thereby forcing the nitrogen, which is also electronegative, to withdraw electron towards itself. So obviously, this species will be more minus R, that is electron withdrawing, than carbonyl groups. Similarly, this is an sp hybridized carbon. Again, this nitrogen will be withdrawing electron and making a vacant p orbital in carbon with a positive sign. So obviously this will also be a minus R group. These are some famous example of plus R and minus R groups. Now sir, now if you think of the conjugate system, the famous conjugate system, benzene ring, JEE loves it also. So I'm summarizing these the effects of these plus R and minus R group on a benzene ring, which is also an example of a conjugate system for us. So at first place, I'm telling you the heading, which is very, very important for you, that in case of benzene, whatever type of resonance it is, plus R or minus R, resonance effect is always operational at ortho and para position. Why, sir? Now let us draw that beautiful resonating structures. Now I've already drawn the sigma cloud because resonance, sigma bonds and nucleuses remain at their place. Who undergoes delocalization? The pi and non-sigma cloud. So let us form this NO2. Okay, sir, there will be a double bonded O and there will be a conjugated pi cloud. So this is the benzene, nitrobenzene. Now, because nitrogen is attached with electronegative oxygen, double bonded, so this will demand electron, and once this electron of nitrogen is gone, so it is now snatching the pi cloud from benzene ring. Therefore, this is a conjugate system, pi sigma pi. What is formed? Oxygen gaining electron, a double bond over here, and a positivity on the carbon. Rest bonds are as it is. So positive charge is at ortho position with respect to NO2. What about next, sir? Cycle has to be completed. So can you see another conjugate system? Yes, sir. Pi sigma plus. Electron always flows from higher concentration to lower concentration. So plus will attract electron. So this will be the next resonating structure. This pi cloud will be moving here, creating a positivity here. This bond is as it is, as it is, as it is. What next? Sir, again, pi sigma plus, electron getting attracted, the pi cloud coming over here, a positivity and a minus. Rest our bonds are as it is. Sir, what about the next structure? Now, an extended conjugate system. You can see what is an extended conjugate system. More alternate positioning, as in minus sigma pi sigma plus. Now electron will move from higher concentration towards lower concentration. Let us form those bonds. Pi, now this pi, rest these two bonds are as it is. With this beautiful 5 resonating structures, which you will always be getting in case of substituted benzene when the group attached is showing resonance effect. Now, because of presence of minus R group, what is happening? Positivity is coming at what? At ortho and para position with respect to the attached group. So resonance, if a minus R group is attached, it will withdraw electron. If I withdraw electron from you, you will get positivity, but positivity is created at ortho and para position. Moving to the plus R group, a famous example, this is aniline. Let me make it aniline. The pi cloud I'm showing with different color. What does plus R group do? It donates, it is an electron donating group. So pi sigma lone pair, electron will flow from higher concentration towards lower concentration. Once this nitrogen has given electron, this electron is not required by the nitrogen, by this carbon, and will be getting transferred to this ortho position carbon. So this ortho position carbon will be becoming a minus, and a double bond will be coming over here with a deficiency of electron. So nitrogen will gain a positive charge. Now rest bonds are as it is. So this is resonating structure 1, this is second. Moving forward, the cyclization will take place, pi sigma minus. Electron will flow from higher concentration to lower concentration. So this minus will form a new pi bond over here. Minus has been accumulated at para position. Rest bonds are as it is. Moving forward, minus sigma pi, conjugate system again formed. So pi electrons are traveling. This is the new bond formed with a minus again at ortho position. Remaining bonds are as it is. Now, after this, sir, minus sigma pi. So going back to the fifth and neutral resonating structure. So again, electrons are back to nitrogen. Cycle has been completed, and this plus R group is showing you resonance is always operational at ortho and para position with respect to the group attached. If I'm giving electron, minus will come. If I'm withdrawing electron, plus will come. But it will come at ortho and para position with respect to the attached group. Moving forward, one very important observation. Benzene as such, sir, we definitely know there is a pi electron cloud. This is the alternate position of pi bond. It can be overlapped this way also, that way also. That's why we make a circle. Why I'm drawing this picture again for you is benzene at first place is from upside also, and carbon, all the benzene nucleuses C6H6, all the carbon and hydrogen are lying on a plane. On upside and downside, benzene is hugely occupied by electrons, so it is an electron-rich species. An electron-rich species is preferably always attacked by what? By a plus, which is having deficiency of electron. Plus will be loving electron, and electron lovers are called electrophile. So this benzene ring will always be preferably attacked by a electrophile, and therefore the maximum reactions of benzene and also its derivatives will be electrophilic attack. Now, if an electrophile gets attached to benzene ring, so aromaticity will be destroyed. So benzene offers electrophile to attack because it is electron rich, so minus. A minus will always attract a plus. But after the attack, substitution will take place, as in wherever this electrophile will come, hydrogen of that carbon will be removed so that at least aromaticity is maintained. We'll be discussing this mechanism in hydrocarbon. That's why I'm making all this picture for you. So first point that we are observing and concluding from this is benzene always preferably tries to do what reaction? Electrophilic substitution. Point number 1. Now, if that benzene is substituted, sir, it may be substituted by a plus R group or by a minus R group. So if I am substituted by a plus R group, I'll be getting electrons at ortho and para position. So that electrophile will be preferably getting substituted on what place? At ortho and para position. And I'm saying that that plus R group is activating the ring towards electrophilic substitution. For example, if you have a neutral benzene, if I am an electrophile, let's say I'm a plus, so this plus will attack this ring, or this plus will attack this ring which is having a complete minus. Sir, more be the minus, more will be the attraction, because plus R group creates actually a complete negative charge. So a complete minus is obviously higher than no charge. There are pi cloud, but there is no excess of electron. This has created a formal charge, an excess of electron on carbon at ortho and para position. Therefore, we say benzene ring is activated by electrophiles. So in such cases, you do not even have to generate those electrophiles. Those electrophiles will be automatically generated because they are attracted by ortho and para position of carbon, because those carbon are having complete negative formal charge due to the presence of plus R groups. Therefore theoretically you will get a lot of questions which will ask you these things in ABCD. That's why I'm discussing this thing in very detail. Plus R groups activate the ring, as an electrophile are, without even catalyst they are formed, and they will attack the ring at ortho and para position. Sometimes the attack can be excessive. They will attack ortho also and para also, because if the electrophiles are created, if the 100 people are coming, they will sit at all the possible places. So because plus R group activate benzene ring, therefore lot of attacks, heavily substitution can take place, but at ortho and para position. Now, if minus R groups are attached to benzene ring, we obviously know electrons are withdrawn, and positive, so plus repel each other. So electrophile will not attack. No. That's why I'm saying, that's why I've given you this, that benzene ring is always surrounded by pi cloud, upside also and downside also. For example, let's say a minus R group is attached. You can find positivity, but still there are presence of pi cloud. The pi cloud is not completely gone. One pair of pi cloud is gone and has created a positivity. So definitely I'm saying, if minus R group is attached, electrophiles are not very eager. They are not desperate of attacking benzene ring. But if at all they are formed, like for example, plus R group are those cases like your dinner at home is ready, but your friends call you and they said some pizza, they said they have ordered some pizza or something, whatever you like, some lavish dish is there. You will leave the food of your home and you will go to that party to have that extra and spicy and maybe your lovable dish. So that is the meaning of activation. When I'm saying deactivated, in such cases electrophiles are forcefully created by catalyst, because they are not desperate of attacking benzene ring, because benzene ring anyway nothing. For that I'm giving you an analogy. Suppose you have not eaten anything, for like 10 days. So if 2 chapatis 6-day-old is offered to you, then you will definitely take that also. So similarly, electrophile does not want to be created. So first you need some catalyst to create an electron, and if at all electrophiles are created, then where they will attack, because minus R deactivated the ring, they will not try to be formed by themselves. You will have to force them to be formed. But if they are formed, those 2 chapatis they will receive where? They will receive those chapati in the benzene ring, because benzene ring is anyway upside also, downside also covered by pi cloud. But preferably they will attack at meta position. Why meta position? Because at ortho and para position there is plus repel each other, but at least at meta position there is no positivity. So when minus R groups are attached, they make the benzene ring meta directing. So moving to third permanent electron displacement effect, that is hyperconjugation. Now, why it was actually needed? The need was given to this world by 2 scientists and is also named as Baker-Nathan effect. Now what they observed is what we already know through the electron displacement effects, that for example, benzene we have recently seen as electron rich species, so it can only be preferably be attacked by electrophiles. So once Baker and Nathan were experimenting the electrophilic attack on these substituted benzenes, obviously through the inductive effect we know that these methyl group will apply plus I to this carbon, and this carbon will in turn increase the electron density at this particular position. So it was expected that because of this plus I, huge plus I groups, this fourth molecule, this fourth substituted benzene should have the highest offer for this electrophile to attack this ring. So it was expected that this fourth should have the highest affinity towards attack of an electrophile, and the least would be of that just methyl group, which is having no plus I. But to a surprise, what our scientist, what Baker Nathan observed, that the very first species was being very much prone for the attack of electrophile. So the order that was observed, that what you expected to be the best, that is the fourth structure, was actually the worst performer to encounter and to cater the attack of an electrophile. People got mad. We have generated so much of GOC, so much of electron displacement, and we are being wrong. So Baker Nathan proposed that there must be something happening with this carbon attached with 3 hydrogens. Now this is actually termed as hyperconjugation, which involves the delocalization of sigma electrons. People started saying sigma cannot delocalize. Why a sigma should get into a delocalization and form a pi bond? Because sigma pi conjugation, a sigma bond, why would try to make a pi bond? This will be rather a contradiction of whole of our chemical bonding. So it was proposed by Baker Nathan that yes, sometimes sigma pi conjugation, sometimes a sigma bond may be converted to be formed a pi bond, and that's why hyperconjugation is also termed as sigma pi conjugation. But sir, still tell us how it is happening. Now, considering a very simpler case, that I have a carbocation. A carbocation is a species which is electron deficient, so it will require electrons. Okay, so this functional group, for according to our IUPAC, the carbon just attached with a functional group is termed as an alpha carbon. So in order for a molecule to show hyperconjugation, what is the first primary condition? That there should be an electron deficient center, and just attached to that center there should be a carbon, and it has to be a sp3 hybridized carbon. Then this sp3 alpha sp3 hybridized carbon, whatever hydrogen it was having, only those hydrogens, out of all those experiments, it was observed that only those hydrogen participate in delocalization. And what delocalization? Their sigma cloud were being donated. It was theoretically proposed that they must be donating their sigma cloud to the electron deficient center. Thereby, if this hydrogen electron is gone, it will attain a positive charge, and the deficiency of electron of this carbon is entertained by the sigma electron of this hydrogen, which recently has formed a pi bond. That's why normally pi cloud undergoes delocalization, which is very normal to us. But when sigma started doing pi delocalization, we said you were a strong bond and became a weak bond, so you must be a crazy guy. To that crazy effect, how do you give a synonym to a crazy conjugation? So hyperactive conjugation. Why the hyper word is coming? Because a strong sigma bond is turning into a pi bond just to satisfy the need of an electron deficient center. Now, if this alpha carbon is having more hydrogens, then this hydrogen may also do that. So this becomes just like a resonance. This becomes the first. After this becomes the next resonating structures. This becomes the other not resonating but hyperconjugating structure, hence shown by that hyperconjugate by the resonance arrow, which both of them can be converting into each other. Now, similarly, this hydrogen can also lose electron and furnish its electron to this electron deficient carbon. So, in total, how many hydrogens are available, how many alpha carbon hydrogens are available to furnish the electrons to an electron deficient center 3. So to this carbocation, we say it is stabilized by 3 hyperconjugating hydrogens. But why I'm saying no bond is formed? Because then we will be contradicting the basic concepts of chemical bonding. So these Baker, Nathan and the scientists proposed that actually no bond formation is taking place. That's why this hyperconjugation is also termed as no bond resonance. But sir, how no bond is taking place? Then why this carbocation is getting stabilized? This is a theoretical, I also give you a theoretical analogy which has been proposed in some other, using some another context by the scientists. Like for example, you have an electron deficient center. To that electron deficient center, you consider a businessman. A businessman which is who is not middle class but an upper middle class businessman. Okay. Now let's say that upper middle class businessman has got a wedding of his daughter. Let's say after 3 days, and because they belong to an upper middle class family, so must be spending some good amount of money in the wedding. Let's say he's going from his shop, a good shop, a well off shop, to his home with huge amount of cash in his hand. Let's say some mishappening has happened and somebody has taken away, it got stolen. So a huge amount of cash stolen by a decent, a average middle class businessman. Although he can arrange that money, but in the same night, if he receives call from 3 friends, friend number 1, friend number 2, friend number 3, asking that businessman, asking his friend that do not worry, we are there with you. If you need any money, just call us 1 hour before and we will give you whatever 10, 15, 20 lakhs, whatever you will be needing for the marriage. So at least at night when he'll be sleeping after that, after whole of that accident of stealing or mishappening that has happened, he must be feeling contented that even if he is requiring those extra chunk of money, he has not taken that money, but that level of satisfaction which those friends have given must provide stability to that particular businessman. If he is having only one friend, no 2 hydrogens, only one friend who is saying you can ask whatever money you want, I will provide. And if he is having 3 friends, the level of satisfaction will be higher. Although why I'm saying he's a sound businessman, let's say in those 2-3 days he must have arranged that money by himself, by having some loans from XYZ places. Similarly, this carbon is having those sigma cloud density. It is not actually forming the bond, it is not receiving them, but just acting like those friends, that if he knows that if he needs, these hydrogen are present. It is the analogy which I am giving you, which the scientist gave and told that no actual bond formation take place, which actually helped us with the chemical bonding contradiction, because sigma in chemical bonding, until now I'm saying sigma never forms a pi bond because sigma is a stronger bond. But this partial hyperactive conjugation actually provides stability, and because of that only this carbon was having 3 hydrogens, and those 3 hydrogens must be getting donated to this sp2 hybridized carbon. Now this carbon is also electron deficient because it's an alkene carbon. So summing up for you, these carbocation undergoes stabilization, attains stabilization through a theoretical effect which is known as hyperconjugation, in which theoretically we are assuming that sigma electrons are actually coming. So because here also actual transfer of electron is taking place, so it also becomes a strong permanent effect. So as of now we are concluding that who is the strongest stabilization effect? Resonance. After that, hyperconjugation, and the weakest will be inductive effect, because it is just a partial shifting of electron, no complete transfer takes place. Now sir, hyperconjugation takes place only at those alpha carbon with which is just beside or adjacent to a carbocation? No. Electron deficient center, that's why I was using. So other cases of hyperconjugation where you will find that alpha hydrogen giving its sigma cloud is when that alpha carbon is connected with an alkene, and sp2 hybridized carbon is also that electron deficient species which is having an pi cloud. So this hydrogen electron can be received and this CH2 will receive that minus. So it is just like resonance, but resonance of only sigma bonded C bond H just adjacent to a electron deficient center. What other electron deficient center shows hyperconjugation? Alkyne attached with such a carbon, benzene attached with such a carbon. This was the actual place from where Baker-Nathan have started this observation. And last is also a free radical can be accommodating, although in case of free radical we will suppose that homolysis will be taking place. So this radical and this radical can do chain termination, and this hydrogen sigma cloud is helping that radical also to be stabilized. So after learning this side of hyperconjugation, now let us also apply that isotopic effect which we have seen in inductive effect. Remember CT3, when tritium, a heavier isotope was there, CT3 was having more inductive effect. But now sir, why we will check inductive effect? We will first check hyperconjugation because it is more strong. Yes. So if you are asked the order of stability of carbocation having tritium, deuterium and hydrogen, what is the correct order of stability of these carbocation? The electron displacement effect was dealing with inductive side of electron transfer. So obviously this will be having more plus I effect. But what effect you will see? Shifting or complete transfer? Complete transfer. So hyperconjugation dominates over inductive effect. And if you check hyperconjugation, which bond can be broken easily? C bond H or C bond T? Sir, tritium is heavier isotope. Hydrogen is the lightest isotope. So C bond H can be broken easily, and hence the sigma cloud can be transferred and delocalized easily to the just attached sp2 hybridized electron deficient carbocation, and hence your correct order will be third carbocation will be most stable, followed by second, and the one that was having highest inductive effect, go and place your inductive effect at home because inductive effect has lost the battle. Hyperconjugation is a stronger effect than inductive effect. Now coming to the, obviously now we already know, but let us summarize by coming to the application of inductive effect. So what can you say about stability of carbocation and radical? Sir, hyperconjugation is also electron donating, so that plus HC plus hyperconjugation will stabilize the carbocation and radicals. For example, this first and second, who is more stable? Sir, if inductive, you will say this is just one methyl group, methyl ethyl, this is bulky group. But no, not apply do not think of inductive first, think of hyperconjugation. So this carbocation is stabilized by 3 hydrogens, while this carbocation is stabilized by just alpha carbon. Only hydrogens of alpha carbon is counted. So how many alpha carbons will be supplying and offering their sigma clouds? 2. I guess 3 is more than 2. So this will be the second carbocation will be more stable. And similarly, like carbocation, alkene is also an sp2 hybridized carbon, that electron deficient center, just like carbocation, alkene is the same. Now, as we know, alkene is an electron deficient species, sp2 hybridized. So for alkene also, what we check for its stability? Inductive effect. But before checking the inductive effect, check hyperconjugation, because sometimes inductive ties. This is also having 1 plus I from this side, 1 plus I from this side. This is also having 1 plus I from this side, 1 plus I from this side. If the alkyl groups gets bigger, inductive has no difference because it drastically reduces to just 10%. So sir, why you are talking of inductive? Check hyperconjugation. That's what I'm telling you. This alkene is stabilized by, now this is a sp2 hybridized carbon. Directly it is connected with this, having 3 hydrogens. So these 3 hydrogens will be offering electrons onto that side. This carbon is having 2 hydrogens. So how many hyperconjugating hydrogen stabilization is reaching to alkene as a system? 5. In this was hex 2-ene, this is hex 3-ene. So over here, these 2 hydrogens and these 2 hydrogens. So this alkene is stabilized by how many hyperconjugating hydrogens? 4, because 5 is more. So 1 is more stable than second. Very, very important and very easy and very recurring question for JEE mains. Now, the last application is stability of benzyl. Sir, as we already seen, benzene, that was the starting point for Baker-Nathan and this concept of hyperconjugation. So for example, this is a carbocation, this is a carbocation. Now this is attached with CH3 and this is attached with C with 3. Sir, but it has to be just opposite. So it will be applying only till here. How it will reach there? Now, in order to show you that hyperconjugative effect of this hydrogen is just reaching to that place like resonance, I'm just taking this benzene and this CH3 group separately. Benzene and that CH3, I mean, if you have more hydrogens, good for you. But for time being, I'm considering if you have one, then let us see that this hyperconjugation is just operating like resonance. So it will be creating electron density at ortho and para position. Let us check. First, let me draw that benzene for you, sir, drawn. Now, that sigma cloud is at alpha position. Okay, we know this hyperconjugation till this carbon only. So let us apply it till this carbon only. Let's say it is reaching over here. This sigma cloud will undergo delocalization. As soon as this hydrogen electron is reaching to this sp2 hybridized carbon, it will not require this pi cloud. So it will be transferred to the ortho position. This ortho position will then be becoming a carb anion. This single bond will become double bond. Remaining bonds are as it is, just the similar way as we have drawn the plus R groups. So minus coming to ortho position. Again, now this is a perfect conjugate system. So pi sigma minus. So now resonance is happening. This minus will be coming here, forming pi bond, creating electron cloud at minus at para position. So this is the new pi bond formed. Remaining bonds are as it is. Pi sigma minus, again a resonating structure. This flow can obviously be predicted. So this is the new pi. This is again minus at ortho position. Going back to the neutral structure. Okay, sorry, this bond as it is. Going back to the neutral structure, pi bond over there. And as soon as it is reaching, that electron will be given back to hydrogen. So the sigma electron is back. Okay, I have removed this pi bond. That's fine. That's why. If electron is reaching that pi cloud, we will getting to hydrogen. No. So this is the new pi bond formed. And remaining bonds as it is. Sir, bingo, back to pavilion. So 1, 2, 3. 3 hyperconjugating structures are telling you that hyperconjugation is just like resonance operating at ortho and para position with respect to the CH3 group attached. So similarly, apply that logic over here. There are 3 hydrogens who will be furnishing electron density at ortho and para position, and because this carbocation is attached at para position with respect to CH3, so it will be receiving electron density from 3 hydrogens. So I'll say it is getting stabilization of 3 hyperconjugating hydrogens, while here number of hyperconjugating hydrogens are 0. So this first structure will definitely be more stable. Now let us predict this exact order of stability of carbocation, which will also be helping us to predict the product produced. So sir, we obviously know resonance, and the extreme case of a resonance is being aromatic. So this is a resonance stabilized system. These are resonance stabilized system. But if you just look at this tropylium carbocation, you can obviously see that because of the formation of that plus, the cyclic conjugation has been reached, and obviously there is presence of 6 pi electrons. So because of this carbocation, it has got its aromaticity, which is extreme case of resonance. So H will be most stable carbocation. After that, sir, resonance stabilized carbocations. This is this is resonance stabilized, that is also resonance stabilized, that is aromatic, this is also aromatic. But this is aromatic because of the presence of benzene, and that carbocation has nothing to do with the molecule having aromaticity. Even if the carbocation is there or it is not, still this compound is aromatic, but that compound is only aromatic. Tropylium carbocation is only aromatic when that carbocation is there. Therefore, that is actually creating that aromaticity to be formed, so becomes more stable. After that, so this 3 degree, because it is getting resonance stabilization from 3 sides, so after that G will be more stable. You will be getting so many questions to predict the product if you know the stability of these carbocations, as promised in the introduction of our slide. So this is how this whole GOC will be used in whole of your organic chemistry. So after that, this F, which is a 2 degree carbocation. Now, after that, I'm holding for a bit because there is an experimental and a logical truth also. Now, let's say this 1 degree benzylic carb, sir, it is resonance stabilized. What about this this I, which I have separately and with different color? Sir, it is a 3 degree alkyl carbocation. Alkyl as in alkyl groups sp3 hybridized system. So what they will be putting, they will be putting plus I. But sir, you said don't see inductive, see hyperconjugation first. Beta, if you are supplied with an alkyl group and you are not told that how many alpha hydrogen it has, then you will be considering it only the I effect. You can, obviously, if the question is being specific, like over here, I am being specific in the first, in the A carbocation, I am saying you have 3, 3, 3, as in you have 9 alpha carbon. Now you tell me hyperconjugation of this tertiary butyl carbocation is due to 9 alpha hydrogens. Do you think of any other carbocation which will have this much of maximum hyperconjugating structures? No, because if this is not CH3 and some other alkyl group, the number of hydrogens will reduce. So because only and only because of presence of maximum possible hyperconjugating stabilization, tertiary butyl carbocation is even more stable. So this, after that, I'm writing A, and it is even more stable than this 1 degree benzylic carbocation, although this definitely is a common sense, is an experimental logic which you should have to learn, but there's a logic also associated with it. Because hyperconjugation is obviously much more dominating than inductive, but lesser than resonance. But the best possible case of hyperconjugation is tertiary butyl carbocation, and that per tertiary butyl carbocation even wins the race, not from all resonance stabilized, but from a 1 degree. From 2 degree, 3 degree, it lost. But it is a winner when compared with the 1 degree benzylic system. So after that, I have written A, and post that I have written E. And then if you have hyperconjugation, good for you. But if you're not the best one, then you are always a loser. So all possible hyperconjugating or 3 degree tertiary alkyl substituted carbocations will be losing the battle from a 1 degree benzylic. So after that, I'm placing this I, and after that, I guess it is quite clear. This is a 2 degree, so B. Post that, this 1 degree, which is C, and obviously the minimum stable will be this methyl carbocation, which I have designated as D. Now, moving forward, sometimes after this, people feel that means, sir, if some plus is creating aromaticity, that is the most stable. I mean, in the mother nature, you will not have any carbocation more stable than an aromatic carbocation, like the one aromatic tropylium carbocation. Again, nature always tricks you. experiments have also shown that one more carbocation, which one? The mystery of cyclopropane, asked by JEE also. This cyclopropane, when is just next to a carbocation, it is observed that not stable from an aromatic compound, but very stable. So this is the big daddy of all carbocations. This becomes because it is stabilized by three cyclopropane groups. This carbocation is stabilized by two, this is by one. So even stabilization by one cyclopropane, when offered to a carbocation, it becomes even more stable than aromatic tropylium carbocation. Now you will say, sir, again, after teaching so much of GOC and concepts, you are saying learn and mug it. No. Now, let us try and understand that what is happening with this cyclic propane, which is stabilizing so much of stability to this carbocation, so that even it is getting more stable from an aromatic compound. First, for that, we just have to first know what we have already discussed. If you get cyclic, if I am an sp3 hybridized carbon, let's say this is CH2, so it is sp2 hybridized. sp3 hybridized. So sp3 hybridized carbon bond pair wants to stay at an angle of 109 degree 28 minutes, approximately 109 degree. So, but sir, if this CH2 is forming a cyclopropane, so through our geometry we know it will be at an angle of 60 degree. So take the difference, divide by 2, you'll get somewhere around 24.5 degree, as in these dotted line shows that a tetrahedral carbon wants its bond pair to be at an angle of 109 degree 28 minute. This whole angle is approximately 109 degree 28 minutes. But this carbon bond pair is forced to be closer to each other. Won't it create repulsion? Maximum repulsion. That's why I have given you before also in GOC1 also that these cyclic compounds are very reactive. They want to react. But sir, here you are saying it is stable because of this. First, let us understand this, that they are at repulsion. Yes. Now, if this is whatever through hybridization you are thinking would have been correct, then what would have been the orbital picture? So how would you be expecting the overlapping in cyclopropane? Sir, this is a carbon, so it will form an sp3 hybridized system. I'll just, because I'm not an artist, so I've already used some beautiful pictures for you. So let me use an laser. So this is a sp3 hybridized orbital. Definitely yes, sir, of this carbon. Of this carbon, again, this is an sp3 hybridized orbital forming this sigma bond. So this along this line you would be expecting your hybridized orbital should lie. We have gone to Mother Nature. To our surprise, what we observed is, and to our common sense also, not actually whole surprise, we already know that there is a Bayer strain through the enthalpy of combustion, which Bayer's has given to the scientist community. So we knew that they are having some repulsion, and because of that repulsion they will be getting geometrically you are thinking that it is supposed to be at 60 degree, but what do you think happens is nature also or not? No. So because we know geometrically they have to be in 60 degree, but because it's bond pair, the electrons, so they will repel, and because of repelling, the orbital clouds will get tilted. So this is a tilted electron cloud picture which was actually getting observed. Now to this tilted picture, you wanted them to lie along the cyclopropane, but world does not work as per you. These are electrons and electrons will repel each other. So because of this bond pair repulsion, this angle will be slightly higher than 60 degree. It will not exactly be 60 degrees. So orbitals must be tilted far apart from each other. Now, this observed overlapping you can also think from your chemical bonding application like that of banana bonding. Probability of finding electron is maximum over here and decreasing along the edges of carbon when you are reaching. Yes, sir. So can't you think of a lobe like this? Yes, sir. Sir, but this lobe is getting by your chemical bonding logic also you can say, sir, this lobe is getting thinner. When a hybridized orbital lobe is getting thinner, as in it is attaining the shape of more and more like a p orbital. So that means percentage p character is increasing. Sir, if p character is increasing, that means s is decreasing. So remember chemical bonding again. See, that's why in bonding I said for understanding good GOC logics you should know chemical bonding also. Although I'm repeating everything, because of the through shape we can say the hybridized orbital is acquiring somewhat shape like a getting thinner who has thinner orbitals, p orbital. That means these hybrid orbital percentage of p is increasing. So if partnership of p is increasing, then obviously it should for in 100% company, if someone partnership is increasing, someone's has to decrease. So if p is increasing, that means percentage s character will be decreased. Sir, but I mean energy cannot be created nor can be destroyed, and hence the energy of those electron clouds also. So this percentage s character will be shifted. Where? Sir, this C bond C, what is the availability? Sir, this carbon has hydrogens. So this percentage s character will be transferring to C bond H, and that will be acquiring more and more S character shape. What does percentage S character do? Sir, percentage S character increases electronegativity. So that means electronegativity of C bond H must be increasing. That means these C bond H must be showing some acidic reactions, because if S character increases, electronegativity increases. Therefore, all these rules were comprehended and made a packet, and the packet is termed as, the logic concept is termed as dancing resonance. Sir, but show us the dance. I'm not showing you the dance, but I mean the logic dance that is happening inside the mind, which is due to high strain in cyclopropane. We know sigma bond cloud behave as pi cloud. It is forming a shape as that of a p orbital. Also, the C bond H electronegativity increases because S character has been increased. Although this is a very advanced logic, this is not going to be asked to you, but yes. Now, because that hybridized orbital is having more and more property as that of a pi cloud. So sir, what does pi cloud do? Pi cloud delocalizes. That is resonance, the delocalization of pi cloud. So when you think of a cyclopropane, why this cyclopropane is stabilizing this carbocation? Do not think of this C bond as sigma bond. Think of it as pi bond. And sir, pi bonds can easily delocalize. So delocalization of pi cloud is also a resonance. But why dancing word is used? Because this C bond C will dance from here till here. So this carbocation has actually received electrons. So this is not also shifting, this is complete transfer. Sir, but this is also resonance, and this is extreme case of resonance, which is aromatic. So why it is winning? Because when this sigma bond is converted to a pi bond, the complete molecule is very happy. Why? As this sigma bond, as this C bond C sigma bond is transferred to this vacant orbitals. What is it, this vacant orbital of? So let's say CH2 plus. That plus will have an empty 2p orbital. So this empty 2p orbital of carbon can easily accommodate that sigma cloud. Sir, that CH2 is given that sigma cloud and formed a pi bond. Sir, but sigma is forming pi. Do not think like that. Why? Because the whole molecule is happy now. Why? Because they were forced to stay at an angle of they do not wish to be at. They wish to be at 109 degree 28 minutes. They are forced to be closer to each other. Although they were forced to be at an angle of 60 degree, they were a bit that's why the tilted orbitals were observed. They were a bit far. But if all the bare strain is released, then this CH2 is also happy, got that electron, and the complete carbon chain is happy because now the carbon chain has been opened up. So this will rather reduce the bare strain. There will be no bare strain if the cyclic chain has been opened up. So the I am again saying this cyclopropane wants to open because of bare strain, but its opening is also also helping this carbocation to such an extent that it becomes even more stable than a aromatic compound. So this C bond C can also give it sigma cloud. So this will become your first resonating structure. Obviously this will be first, this is second, and if this is given, so this can also be given. So this cloud can also be given. So how many resonating structures you find? 3. And this resonance is actually termed as beautiful concept of dancing resonance. All these things will be very much applicable to all our even mains questions, although they'll be good questions, but mains ask these questions and will be high application of all of your organic chemistry of class 12 that will be starting in the next one shots. Now moving ahead, one more alkyl halides, alcohol phenol. I mean, this is more of that detail which in later chapters you will be requiring, and once they are taught, then a need of GOC arises. So I'm finishing that GOC, a very small topic. Now, what is Betts rule? When you have a ring with 8 or more than 8 members, then actually sp2, what is an sp2 hybridized system? It's a trigonal planar system. So if you have 8 or less than 8 members in the ring, not continuously, in total, like for example over here there are 6 members and this is the 7th member. So even if you have 8, then in that particular case, because of crowding, any sp2 system, sp2 carbon or any sp2 hybridized atom, because sp2 system is a trigonal planar system. So if you want to become an sp2 hybridized system, you have to take a geometry of trigonal planar, but these all molecules cannot come in a plane. Because of you, all the nucleuses will not lie in a plane, so you cannot restrict them. So if you cannot restrict them, you will not be formed, you are not invited to the party. So what I'm saying is, let's say this carbon, I mean, let me remove that. Let's say I have nothing over here. I'm giving an example that why I'm telling you. For example, you have a chlorine substituted here over here and NaOH is attacking. So we know, sir, Cl is removed and OH added. But Cl, when Cl gets removed, a carbocation is formed. So, but that carbocation will make this carbon an sp2 hybridized system because it is forming 3 sigma bonds, no lone pair. So can a carbocation be formed over here? No. So do any substitution will be offered at this bridged position? Now this carbon is known as a bridged carbon because it is acting as a bridge between different rings. This becomes the first ring, this becomes the second ring. So what is a bridged carbon? Which is a junction for 2 rings, and at that particular bridged carbon no substitution can take place. Why? Because if there will be a formation of carbocation, then it will be a trigonal planar species. It cannot form a trigonal planar species because of me, all the people will not come in plane. Somebody is not Shah Rukh Khan that everybody will follow him. So this guy cannot be formed, therefore no substitution. So if someone is asking you whether this carbocation is stable or not, you will say leave about stability. It will not even be existing in nature, even for fraction of second. Similarly, can you find an alkene over here? No, this alkene will then make this carbon also sp2 hybridized. if it will be an sp2 hybridized carbon, it has to come in a plane, but it cannot come in a plane because these so many members will not allow this carbon to be coming in sp2 hybridized trigonal planar geometry. So this will also not be existing. Such alkenes are also, if given to you, they are not possible, not stable. Similarly, what will be hybridization of this carbon? Sir, 3 sigma bonds, no lone pair, odd electron is not counted in steric number calculation. So this is also sp2, so this will also be not existing. Now, people close their eyes and say, okay, sir, in bridge position, nothing possible. I'm not saying nothing. sp2 hybridized is not possible. This carbon, so 3 sigma bond, 1 lone pair. So this carbon is actually sp3 hybridized carbanion. sp3 hybridized carbanion is a 3D structure, trigonal, tetrahedral geometry. Geometry is tetrahedral, but shape will be trigonal pyramidal. And it is not forced to come in a plane, so this can easily be formed because rings, everybody can lie in 3D, so they'll be having sufficient distance from each other. So this is definitely possible. What about that one? Let's say that carbon is a nitrogen. Sir, again, it's sp3 hybridized system. This much VSEPR theory we know. So because it is not having a planar geometry, so this can also be formed because this is not forcing anybody else to be coming in its plane. So this bridged carbon can never be, or bridged atom can never be a planar species, can never have an hybridization of sp2. Now, sir, do we have some other applications also? Yes. For example, I'm giving you a statement. This is a carbanion. Okay, sir, you just said carbanion is possible. So never close your eyes. Always invest your mind. Sir, you said carbanion is possible. So that means this is possible. So the statement which I'm trying to trick you with is, let's say this carbanion, so you can find resonance also. Sir, how? Because you know there is a formation of conjugate system. Sir, minus this minus is possible. We have just read. So minus sigma bond pi. Sir, pi sigma minus is a conjugate system. Moreover, this minus is at carbon. New pi formed. And now minus is on oxygen. Sir, negative charge on more electronegative atom is more stable. You told us. Just go to the structure. Is it an alkene? Yes, sir. If this is an alkene, then this carbon, the bridged carbon, is forced to be in sp2. Yes, sir. sp2 possible? No, sir. So leave about resonance. I said you can exist, but you cannot undergo resonance. Why? Because that will make you an sp2 hybridized carbon. So your pi cloud forming a pi bond is not allowed by whole system, because then you will be planar and you are not allowed to come in planar, because we will not fall as per your wish. You are not our boss, you are just a carbon as we are. So because this is not possible, so resonance stabilization is not possible. A very good application of Brett's rule. Moving forward. So moving to acidic and basic nature comparisons of alcohols first, we definitely see this phenol, when forming phenoxide ion, is a highly resonance stabilized system, because this O minus is a plus R group for the benzene ring, then benzene is a minus R group for that O minus. So minus R group will stabilize this excess of minus and will form a very stable conjugate base, which is called phenoxide ion. And because of this fact, phenols are always stronger acid. Not from all. Among organic acids, obviously carboxylic acid is much stronger acid than phenols. Any carboxylic acid is stronger acid than phenol, because in carboxylic acid you get COO minus, which forms equivalent resonating structures, and equivalent resonating structures provide maximum stability. So all carboxylic acids are obviously stronger acid than any of phenol, but this phenol is also forming phenoxide ion, which is also resonance stabilized. So it is a stronger acid than its counterpart. Counterpart as in, this is an aromatic alcohol. So let us compare with an aliphatic alcohol and even water. Because when water and aliphatic alcohols are compared, you can obviously see there is a presence of an alkyl group which is applying plus I effect. So sir, this O minus will be much dramatically and drastically wanting to give electron, so it will be a strong base. it will be wanting to give electron, and if this wants to give electron, then equilibrium will be shifting to backward direction, which will make any aliphatic alcohol even weaker than water, because at least this O bond H is not pressurizing that O minus to a larger extent. So hydroxide is not as strong base as an alkoxide ion, and because it's a strong base, so equilibrium will be shifted to backward direction, which will make all aliphatic alcohol to be weaker acid than water. Now, why I have left that space is because of a experimental fact that only one aliphatic alcohol, which is the first aliphatic alcohol, which is methanol, although methanol is also having this CH3 applying plus I, so this definitely is weaker than phenoxide, and so phenol are always stronger acids than any aliphatic alcohol. But only methanol, due to experimental value of the dissociation constant Ka when observed, it is slightly better than water. Moving forward and discussing about carboxylic acid, we can apply the same analogy. If you compare formic acid is having nothing. I mean, to the resonance stabilized conjugate base, which is the carboxylate ion, hydrogen is not giving anything also, taking anything also. Electron withdrawing group will increase the acidic nature because it will stabilize this conjugate base. Like this hydrogen is applying nothing, but to this carboxylate ion, benzene ring is doing what? Sir, we know this is a minus R group, that means benzene is a plus R group. So if we compare this benzene ring with respect to hydrogen, we will say that it is obviously a plus R group, that means electron donating group. So electron donating group will destabilize this carbanion. Because this is destabilized, will not be formed in comparison with the carboxylate ion given by formic acid. So formic acid becomes a stronger acid than aromatic carboxylic acid, which is benzoic acid. But when you compare benzoic acid with another, this is also an aliphatic acid because not having aromatic ring, but all other aliphatic acid will have alkyl group. This alkyl group will apply plus I effect, and this plus I effect, my friends, is electron donating nature. So they will in fact destabilize the carbanion. But you will say, sir, this is also destabilizing. This is destabilizing, and resonance is always a higher in magnitude. But that resonance was I was comparing with respect to formic acid. They are destabilizing, but it is also trying with the minus I of the SC. This double bonded carbon is an sp2 hybridized system, not of one carbon, of 6 carbons. So don't you feel this 6 sp2 hybridized carbon will also have a minus I effect on this carboxylate ion? Yes. I'm not denying to the fact that I said resonance is a stronger effect and inductive is a weaker effect. So because of resonance, this guy has lost the battle from formic acid. But I have been trying and giving my paper, and I have been practicing. I have started very late. The plus R is like a destabilizing group. So you may have started 1 month back, but at least now you have started. And because you have started, so you will be getting at least some good marks as compared to those people who have not even started, because this guy, this alkyl group, is just an electron donating group providing nothing to this carboxylate ion, and in fact by that plus I nature it is destabilizing this carbanion. I have also destabilized through plus R, which is a dominating effect, but at least with my minus I am trying to stabilize it also. So when aromatic and aliphatic are compared, aromatic wins the race because this minus I is better than plus I of alkyl groups. Although this trickles and disturbs students, or while comparing this you are seeing resonance, but few logical things you have to keep in your mind, and they are, if you say, there are some facts also, because what theory you have to consider, sometimes you have to remember that also. So this minus I will be making this aromatic carboxylic acid a stronger acid than any other aliphatic acid. So aliphatic acids will be weakest acid. Moving forward, comparing about the basic nature of amines. So Obviously, I mean, now this becomes very quite evident to us. Who is a base who can donate lone pair? So ammonia is a stronger base than whom? Then aromatic amine, because this lone pair is not at all present in nitrogen. This is localized in the ring because this is a plus R group. So if you are plus R, you have donated your lone pair. So the probability for you to giving out these lone pair is less as compared to ammonia. So ammonia is a stronger base, and we have already seen alkyl amines. Now the R group will be helping nitrogen because acidic nature decreases, but basic nature increases by electron donating groups. So this R being an, with this we have already done. So alkyl amines are stronger base than ammonia, while ammonia is a stronger base than any of the aromatic amines. A very beautiful case which you will be getting so many questions. Few of them I've taken example for you. Now you have to tell which is most acidic. I guess this is quite easy. This is an electron withdrawing group, so this can also be acidic, this can also be acidic. So you again have that electron withdrawing group, so this can also be acidic, this can also be acidic. Obviously when you give H plus, carbanion is formed. So what carbanion is more stable? 1 degree. After that 2 degree. Least stable is 3 degree because minus do not want to get extra electrons, but just checking options first. So here also, so this can also be acidic, this can also be acidic. Over here, oh, there is presence of 2 electron withdrawing group. So this electron withdrawing group will make this acidic also, this one also, this will make this also. Sir, that means this CH2, this guy is getting electron withdrawing nature from this side also, this side also. So if minus would be coming over here, it can go to resonance at this side also and that side also, which is double in number. Rest of the options are having only one side of electron withdrawing group, but this is getting stabilized by 2. I mean, once it will give H plus, it will form carbanion, and carbanion will be getting stabilized by resonance from this side also and this side also. So easy application of resonance effect. Who is a strong acid? Now again, that's this acidic. Now we can clearly see, sir, the 1 electron withdrawing group, second and third, so 3 electron withdrawing group will make this carbon very acidic. So this H will be going like anything. Here there are 2 electron withdrawing groups, so this is also acidic, but 3 is more, so this is winning. Then option D. Yes, an sp hybridized system, but no, you are just a electronegative carbon. You are not getting any help of resonance, so you lost the battle, although you are also acidic, but these are having strong minus R groups. And over here there is only one, so obviously B is your best answer, strongest acid. Moving ahead. Now you have to tell the order of basic strength. So who is a stronger base? Now sir, ionic equilibrium we have seen. If acid is strong, conjugate base will be weak because equilibrium will be shifting forward, so will not come back. So strong acid, weak base. Weak acid forms a strong base. So applying that theory, how? Sir, we know, call their acids, call their parent, call their daddy. Who is acid of HCl? Cl minus, sir, it's HCl. Okay. Who is daddy of CH3C double minus? Sir, ethanoic acid. Okay. This is aliphatic alcohol, ROH. OH minus, give H plus. Sir, water, we have already done that. See, I mean, simply questions are asked. So HCl is a mineral acid, strongest acid. So its conjugate base will be weakest. So Cl minus will be weakest. No. Cl minus weakest, yes. Now after that, now they are organic acids. So who is a stronger acid? Carboxylic acid is a stronger acid than water, although water is not at all acid in comparison to mineral acids. Organic acids are weak acids, they are now compared with water, but carboxylic acid is a stronger acid than water because carboxylate ion is resonance stabilized equivalent resonating structures, remember. So obviously carboxylic acid is a stronger acid than water. So because carboxylate, so its base will be weak. So after that CH3C double minus should come. Yes, both are tie. So the question is all not giving you tie also in that. So you have to go to ROH and alcohol. This we have recently done. ROH is a weak acid than water. So if it is a, who is a strong acid among aliphatic alcohol and water? Water. So water is a strong acid. That means OH minus is a weak base than RO minus. And this you can also think, if you are a base, this minus has to be donated. This RO minus will be even increasing electron density at oxygen. So this will be the strongest base. So OH minus is a weak base, RO minus is a strong base. You can do it by any analogy. So OH minus is weak, RO minus is strong. The option B is right. This is also wrong. Moving ahead, a very beautiful question of whatever we have studied. Moving ahead. Again, acidic nature. Now, when no resonance or such electron displacement application is there, then go to chemical bonding. There how? This is a carbon, yes, sp hybridized, s character 50%. This is a carbon, yes, sp2 hybridized, s character 33%. More be the s character, more is electronegativity. This is sp3. This is sp3. So they both are tied as per hybridization state. So who is strongest acid? 1. So 1 is strongest acid. 1 is strongest acid. These two options are gone. Now, after that, who will be strongest? It's 2. So 2, 2. Okay. Fight is between 3 and 4. Sir, you are also sp3, you are also tie. Now, although alkanes are not at all acid, but in your weakest case, if you are earning 1 rupee, then somebody is earning 0.5 rupee. Then if you are earning 1 rupee per day, you are rich than the person who is earning 0.5. Although nobody can have even 1 roti at night, but among these alkanes, this carbon is attached with 1 CH3 group. So it is a this becomes a 1 degree carbon, while this becomes a 3 degree carbon. What does alkyl group do? They apply plus I. So plus I is electron donating. Electron donating decreases acidic nature. So this becomes relatively a stronger acid. So 4 is relatively good. 4 is relatively good and 3 is the weakest. So A is your answer. Moving ahead. Now, order of basicity. Now, basicity, what is a base? Again, sir, base is a species which can give electron. So who can give electron easily? Let us check. This C minus, oh, it is getting electron cloud from all the places. So if the conjugate base is strong, then it can hold the electron, and if it is weak, it has to give electron. So this is quite weak base, so it will definitely try to give, and if it will try to give electron, it will act as a strong base. So this is a 3 degree. Okay, sir. Now again, because there is no now what I told you, first check hybridization state also. This is a 3 degree, but it is an sp3 hybridized carbon. What about this? Sp3. What about this? Sp. What about this? Sp3. What about this? Sp. Now, sir, sp hybridized system is electronegative, so they can hold the electron because it is electronegative. And because they can hold the electron, so they will not furnish those electrons. So these two will be the weakest basicity. They will be weakest base. So among 3 and 5, who will be weakest? Sir, C triple bonded with C. I mean, this C can also hold, that C can also hold, but that C minus is triple bonded with an even more electronegative nitrogen. So it can hold to the maximum extent. This Cn minus can hold its electron to maximum capacity and will not give. So this fifth will be the weakest base. This fifth will be the weakest base. Fifth is weakest, fifth is weakest. No. So you are again ended. So you have just to compare the topper. So who is the topper, first or third? First is a 3 degree carbanion, and third, okay, you have to compare. Oh wait, there is not even a comparison, because after this will be coming. So weakest is 4 and the next weakest will be third. Weakest is 4 and the next weakest will be third. It is saying it is coming at the top. So obviously A is your answer. So I've just using method of elimination, which you should also do in your paper. But discussing every question, I mean discussing other options also. So 5 and 3 done now. So 5, 3 done, 5 done. Now these are all sp3 hybridized. This is a 1 degree amine, 1 degree carbanion. This is a 3 degree carbanion. So 3 degree carbanion is in a dramatic hurry of giving electron because it is having so much of supply. So among 1 and 4, 4 is stable and hence a weak base. This 1 will be a stronger base. So 1 will be stronger than whom? Than 4. Sir, what about 2? In 2, although this is sp3 hybridized, but you can also see that this minus can go to conjugation. I mean, this can even be shared by this carbon, although this carbon will also be an sp3 hybridized carbon, but there is a sense of resonance stabilization. Therefore, this minus can also be holded, but by sp3 hybridized carbon, which is itself not having the capacity to hold. Who has the higher, if you're having just carbons only, then which carbon will be having highest capacity? That you will see through the hybridization state which we have done. Moving forward. Good question. But these are many times asked. So try and understand the logic and revise the logics. Now, correct order of basicity. So, acha, for these type of question, I'm telling you one thing at first. If two people are going for a fight, and if one person is going, I'm not talking of heroism in films, and I'm talking practically. So if two people are coming from this side and one person is coming from this side, then obviously who has the higher tendency to beat? Although that two person may be, I mean, you do not have to compare the strength. I mean, that's why I'm saying I'm speaking practically. So point is, there are two nitrogens and there is presence of only one nitrogen. So two nitrogens will definitely be having two lone pairs. I'm not saying those lone pairs will be delocalized, aromatic, not getting, but the family is having two atoms which are having one lone pair each. So more be the donor atoms, stronger is the base. More be the functional groups, stronger be the action of that particular functional group, although that action may be larger or lesser. But two companies will earn obviously double. Now, if there are two companies compared with another two companies, then you can go to the balance sheet that what you have done, what expenses. But if two companies are compared with one company, generally the two will have a higher balance sheet because they are of equivalent nature. If this is also nitrogen, these are also nitrogens, and nitrogen will also only give the lone pair. So with that analogy, I'm telling you, fourth will be the strongest base, because you are, so fourth will be strongest, fourth will be strongest. So again, you see, in JEE mains question, you always end up with 50-50. In all the questions, just by knowing one logic, you directly eliminate two options. Now, so fourth is the strongest. Why? Because two donor sites are there. Now, coming to this, so this lone pair is not involved in aromaticity, because pi cloud, the Huckel's rule is done by these 6 pi electrons, while this lone pair is of pyridine is not participated in aromatic nature. This lone pair is not at all available for donation. Why? Because this lone pair will make this ring an aromatic ring. So this will not at all participate because this is aromatic. And over here, this nitrogen is also available. But you are also nitrogen, I'm also nitrogen. My lone pair is also available, your is also available. Now do what? Check their hybridization state. So its hybridization state is sp3. This is sp2. So this will not at all give, so weakest base, so 2 will be weakest. So I got my answer with this only, but because we are practicing, so let us compare 1 and 3rd also. sp3 and sp2, which is having more s character, this is having more s character, more electronegativity. So I will try to give electron to a lesser extent. So 1 will be weaker than 3rd. So 1 is weaker than 3rd. Moving ahead. Now, I'm discussing most of the questions which are just now have came, because their probability of coming also is very high. Now, you have, now the acids are marked as ABCD. You have to say which is a stronger acid. Now again, go to the functional group. This is COOH. So this H is hydrogen of a functional group, which is among organic compounds is even called an acid, carboxylic acid. That's why it's even called an acid, because it is a stronger acid. So this HC will be strongest. HC is the strongest. No. Yes, yes. So okay, this time we eliminated only one. Now this is next to a, okay, but this C is also a carbonyl group and strong electron withdrawing group. Do you find any strong electron withdrawing group? No. I mean as strong as carbonyl, because once this H plus is gone, this minus will be in resonance with the carbonyl group. very stable resonating structure. So after that, D will be more stable. So D will be more stable. So D will be more stable. So this is also gone, left with two options. Now coming C gone, D gone. Now comparing A and B. Now this is easy. This is also carbon. This is also carbon. This is an sp hybridized carbon, while this is an sp3 hybridized carbon. So sp hybridized carbon is obviously more s character, more electronegative. So after Ha will come. So after that, Ha, and weakest is Hb. So B is your answer. Moving ahead. Now, this is a very the simple question that we have done, that who is the strongest acid? Formic acid is the strongest acid, and as alkyl group increases, electron donating nature increases and acidic nature decreases. So formic acid becomes strongest, and as alkyl group increases, acidic nature decreases. A very easy question, a JEE 2024 question. Moving ahead. So moving to this next JEE Mains 2023 question, it is asking to compare acidic nature of substituted phenol, but many students miss this. It is asking to arrange in order of values of pKa. Now, if acid is strong, if acidic nature is high, then Ka value, that is dissociation constant, will be high. But pKa will be small because through in ionic we know pK is nothing but minus of log of Ka. So if Ka is large, then value of pKa will be small. So we have to compare acidic nature only, but the value, the order will be reversed, because if Ka is high, then pK will be less. So let us first estimate the acidic nature. Sir, phenol acidic nature is increased by electron withdrawing group. So over here, para position has nothing, hydrogen. Over here, substituted nitrogen. Substituted, I mean nitrogen, but this nitrogen will be applying what? Sir, it will be doing plus R. Plus R is an electron donating group. So we'll decrease the acidic nature. Sir, this is a beautiful NO2 group, will apply minus R, electron withdrawing group. So electron withdrawing group will withdraw electron and will increase the acidic nature. This is a carbon, but it will be having one hydrogen, so it will also be a electron donating group due to plus hyperconjugation, but that plus hyperconjugation will only because of one C bond H. So who is winning the race? Sir, electron withdrawing group makes acidic. So third becomes the most acidic substituted phenol. You are destabilizing, at least hydrogen is not doing any bad stuff. So simple phenol will be the next stronger acid. You are also bad, but you are destabilizing, you are giving electron through a stronger plus R effect. You are giving electron but through a weaker plus hyperconjugation. So fourth will be next and least would be second. But this will be the order of acidic nature and Ka. So trend for pK will be opposite. So 3 will be least, then 1, then 4, then 2. So obviously you can find B is your answer. Now, some people get confused, or not confused actually, questions confuses them, and the answer for that confusion is sometimes resonance effect is sterically hindered, and this effect, although not very much asked by JEE Mains, but a highly probable logic which has came many times, but many students miss it. It is not any strong logic, so just investing few time for that also. Now, what is the steric inhibition to resonance? Let me first tell you why it is required. So again, doing a question. This is also substituted phenol. Okay, sir. Now, in this substituted phenol, let us estimate acidic order. Sir, this is phenol. Okay. Methyl, ortho, para, meta substituted methyl of phenols. Sir, methyl is what? At ortho and para position, CH3 or any group which is applying resonance resonance is always operational at ortho and para position. We know CH3 applies plus hyperconjugation. So that plus hyperconjugation will be applicable at ortho position and at para position. So plus hyperconjugation is an electron donating group. Electron donating group will decrease the acidic nature. So obviously you are decreasing. So if phenol is not having anything, that is a stronger acid. And what about this methyl? Although this is at meta position, so meta cannot be resonance or hyperconjugation operational, but because it is CH3, it can at least apply plus I. So now what I'm saying is, because this phenol is not substituted by anything, so it becomes the strongest acid. Electron donating group has decreased the acidic nature. Yes, sir. But this has been decreased by strong hyperconjugation effects, while this is decreasing but with weak plus I effect. So this will be relatively better. So this will be second strong acid. Among these two, hyperconjugation, you have also got hyperconjugation, I have also hyperconjugation, so both gets tied. Now tie break will be done by, at ortho position, plus I is large with respect to para, because inductive is distance dependent. This is closer, so we'll be applying higher plus I. This will be applying lesser plus I. So relatively this will be better, and least will be that guy because it is having hyperconjugation and strong plus I also. Electron donating group decreases stability. With this we all know. Now, why SIR, sir? Then SIR because in case of carboxylic acids, because they are big, this C double bond O bond OH is a huge. This OH was not having that inhibition because it is small. So whenever this carboxylic acid is ortho substituted, carboxylic acids also and aromatic amines also, they get this ortho effect. People learn this ortho effect. It is a common sense. When this carboxylic acid, because it itself is a big molecule, it's a big group, so it is a planar molecule. What does this carboxylic acid gets? What offer benzene is giving to this carboxylic acid? They are in resonance. Why they are in resonance? Because the pi cloud of benzene, because this is also trigonal planar, because this carbon will be sp2 hybridized. So the lone pair of this C double bond O can delocalize and do resonance because lone pair are parallel to each other. But when this carboxylic acid is ortho substituted, I'm just speaking of groups present at ortho position. So those groups will be creating crowding also. So this triangle which was there in the plane with the ring will not be able to be in the ring, because now this crowding will be hampering these groups. And in order to, when you are crushed by a crowd, what do? You step aside, you give them way so that you feel comfortable. Similarly, because of the bulkiness of this group present at ortho position, this plane will rotate by an angle of 90 degree, because the triangle was made like this. So if the triangle is made like this, then if a group is over here, I will not feel its repulsion. So instead of having this planar geometry, I'll have this planar geometry. But because of rotation of my plane, now my pi clouds are not parallel with the pi clouds of benzene ring. So if they are not parallel, the delocalization will be sterically hindered. So whatever resonance effect you apply, do not apply. And if that resonance effect, what resonance effect has been cancelled? Sir, COO is a minus R group. So if it is a minus R group, then the ring was actually a plus R group for COOH. Plus R group as an electron donating group. That's why carboxylic acid, because of plus R of benzene, were weaker acids than formic acid, remember. So if at all I am not in resonance, I'll be not receiving that plus R from the ring. So obviously, if electron donation has been reduced, your acidic nature will increase. What some students do is they mug up that due to ortho position, acidic nature increases. Actual reason is this. But yes, due to ortho effect, because the plus R has been detached, so now carboxylic acid is subtracted from an electron donating group, and if electron donating group is removed, because electron donating group was decreasing the acidic nature, now the acidic nature will be increased. So ortho substituted carboxylic acids are always weaker acids, no matter what type of group it is. If this group is minus R plus R, you keep your resonance effect at home, because resonance is not at all reaching to carbox COOH group. So even if it is a plus R or a minus R group, it will have no impact, because of presence of this group, the whole resonance given by plus R given by ring has been deleted. So if plus R is deleted, I'm happy as an acid. Therefore, ortho substitution will always increase the acidic nature of ortho substituted carboxylic acids. So this I have written also a point for you, but I mean, this is quite although common sense, but this type of questions you cannot expect just directly. Means that when these ortho groups are second period elements, small elements like OH, OR, NH2, H, F, then in that particular case, because the crowding second period elements are doing is not large, so in those cases ortho effect is generally not considered. But when it is considered, I'll just give you an example. It is here only. Now, just in the similar fashion, if now we know ortho effect, that carboxylic acid when substituted at ortho position becomes a strong acid, because resonance is cancelled, resonance is inhibited. So comparing again methyl substituted. Now methyl, so you will say, so carbon is also second period, but methyl is a tetrahedral geometry. That tetrahedral geometry will create bulkiness. So ortho substituted carboxylic acid will become strong acids. Now, because this is ortho substituted carboxylic acid, so it will become the strongest acid, because the whole plus R of the ring has been cancelled. Now, after that, apply whatever logic you know. What logic you know? Acidic nature is increased by electron withdrawing and decreased by electron donating. Methyl is an electron donating group, either by plus I or plus hyperconjugation. Normal benzoic acid is not having anything, so it will be coming second, but it will coming second. This has come first because of ortho effect. Now, among meta and para, sir, at para it will be applying plus hyperconjugation, but here no hyperconjugation, just plus I, which is weaker. So electron, it is also donating, but very little, because inductive is little. So this will be third and that will be last. Again, I told you this ortho effect is also operational for amines. So, sir, how? Now, crowding is there. You very well know that. Now, suppose this is actually methyl substituted aniline. Now, because of, I mean, some student learn it also. Like over there, I'm giving that trick also. What trick? Or for carboxylic acid, ortho effect did what? Increases acidic nature. So here also it will increase acidic nature. So it will increase acidic nature as in decrease basic nature. So ortho effect also always increases acidic nature. I mean, sometimes it will be done, but let me give you logic also. Now because of crowding, again the inhibition is there, but in case of NH2, because NH2 is not a planar molecule like COOH. I'm not saying the complete resonance is hindered. I'm not saying anything of that sort. But yes, ortho effect is there. And what is ortho effect doing? It is making it a weak base. Why? Because if I have to be a base, I have to give electron. In order to give electron, I have to invite that molecule. So any molecule, if invited, let's say any H plus, let's say any H plus is invited. If it is invited, then only I will be able to give my electron. The invitation is only hindered. Why? Because there is so much of crowding. So how can that nucleus will be getting into in between these bulky groups, because there is so much of crowding. So because of so much of crowding, the furnishing of lone pair of nitrogen to the H plus will be decreased. Therefore, basic nature, I'm writing this, of amines decreases due to ortho effect. Ortho effect. This is a point I want to keep in your mind, and this picture will help you to understand why it is happening. So it will, ortho effect will make it a weaker base no matter what, no matter what group is attached. Now, because it is a weaker base, then it has lost the battle. Now, for other substituted aromatic amines, you apply the same logic. What logic? Now I'm talking of basic nature. So basic nature increased by electron donating group. CH3 is an electron donating group. At para position, it will be applying strong hyperconjugation, so strongest base. At meta, not hyperconjugation, but at least I'll be applying plus I. So plus I is also electron donating group, so a better base than normal aniline, which is not having any sort of such electron donation effect. Moving forward, moving to electromeric effect, our last electron displacement effect, and as you obviously should know that it is nothing but application of inductive effect. Just like inductive, it is also of two types, plus E and minus E. It is temporary effect and only operational at the time of attack. Electromeric effect is only observed when the substrate, the reactant molecule, is having multiple or pi cloud. So what is plus E effect? If I have a plus as in an electron loving species, as in an electrophile like an H plus will be attracted by the electron cloud of an alkene. So minus and plus will attract each other. Although we say H plus is the attacking species, but the arrow has been, I have made that arrow from obviously higher concentration of electron towards lower concentration. So this pi cloud will approach this H plus. And what does plus E effect suggest? It is a temporary effect which happens only when the attack is happening, hence temporary, because all the time attack will not happen. It will just happen at the beginning of a reaction. And what does plus E effect suggest? It is a common sense. This is an electron deficient species. It will withdraw electron. So if it is attached with, let's say, with the middle carbon, then that pink electron of hydrogen has came from where? Obviously the other carbon atom has lost that electron. So the statement says that the attacking species is attached to which carbon atom or whichever site the pi electrons are transferred to, that site only. But sir, you had made two options. That's why I'm saying it's a common sense. You tell me this attacking species will come here or here. Sir, if it is coming here, electron has been lost by this carbon. So this carbocation is a 1 degree carbocation. This carbocation is a 2 degree carbocation. Obviously, you know 2 degree carbocation is more stable, so it will be formed and it will not be formed. In organic chemistry, we will not say that is not happening. Most probable product is formed in the larger percentage, so it will form a larger product, while this will form a minor product or very less percentage of product. So this forms minor product. So if questions is asking, let's say question says this is attacked by HBr, so H plus attacking pi cloud forming this carbocation, and Br minus will be adding up over here. So this is knocking the door for the later organic reactions chapter, and whole of that organic reaction mechanism will obviously be requiring these common senses of GOC. Moving to the minus E, sir, in that case minus during minus E effect we'll be taking an attacking species which will be negatively charged. Negatively charged will be an positive loving species, so will be termed as a nucleophile. Obviously, it will attack to a substrate which is having pi cloud, because electromeric effect only deals with those substrates which have pi cloud. So now where it will go? Again, a common sense. This is Cn minus ion. It will attract what? Plus. Sir, this has a polarity. This is a carbonyl carbon. So this is minus and this is plus. So this minus will be coming to this carbon plus. When it is coming, it will bring its lone pair also. Sir, why you are only drawing that arrow from carbon? Why not nitrogen? Both are having lone pair. Nucleophilicity, as in your ability to give electron, is where to a larger extent. Sir, negatively charged species represents a formal charge. So a charged species is obviously a better donor than an uncharged species. So because carbon is a charged species, it is having a formal extra minus, while nitrogen is a neutral species. So charged is always a better donor than uncharged. And if I'm donating to a carbon, I'm called a nucleophile. If I'm donating to a H hydrogen, H plus, I'm a base. Both base and nucleophile donates electron. So if it is donating to carbon, this Cn will be attaching here, and this pink color pi cloud will be reaching to O minus. So in minus E, what we say, attacking species is attached to that carbon, then pi electron is gone to the other atom. I mean, this is a common sense of all the electron displacement effect and the GOC theory which we know. And obviously the nucleophilicity is a JEE mains question only, that which has higher nucleophilicity. As I said, charged is always a better donor than uncharged. So this is charged, so a better donor. This should be better donor, so this is wrong. This should be a better donor, so this is wrong. Both are charged, but fluorine is more electronegative, so can hold electron. So this will be a better donor, so this is also wrong. Moving forward and saying thank you. This is Gaurav Singh Arora signing off with GOC-2, but you guys have to revise. Personally, when I watch some lessons, some things from where I wish to learn, make a 2x speed and have very sound revision. Because I have exceeded quite a lot of time in GOC1, therefore I'm restricting GOC2, because we have to deal with reaction mechanisms, nucleophilicity, basicity orders, application of hydrogen bonding. These all topics will be dealt in the chapters where they will be required in the later chapters of organic chemistry. Till then, revise and practice hard. I will see you in the next one shot. Thank you.